This is 30 prehistoric events that never made it into your textbook. Number 1. The Chicxulub Impact. 66 million years ago, in the shallow warm sea that sat over what's now the Yucatan Peninsula in Mexico, it was an ordinary afternoon. Turtles drifted in the lagoons. Ammonites, those coiled shellfish that look like spiral ram's horns, hung in the water column. Small feathered dinosaurs picked along the coastline, and out in the deeper water, marine reptiles cruised the same way they had for tens of millions of years. Nothing about that afternoon suggested it was the last one of its kind. Then a rock about 6 to 9 miles wide came in from space. We call it the Chicxulub Impactor, named after the little town near the center of the crater it left. And to picture the scale, that rock was roughly the size of a mountain, moving somewhere around 12 miles a second, so fast that the air in front of it didn't have time to get out of the way. It hit the seafloor, punched through a couple of miles of water, then punched through the rock underneath, and carved out a hole in the crust more than 100 miles across. The energy involved is the kind of number that stops meaning much once you write it down. Estimates put it at billions of times the energy of the bomb dropped on Hiroshima. But you don't need the number to picture what it did. Everything within a few hundred miles was gone in the first second. The impact threw a curtain of molten rock and vaporized seabed straight up out of the atmosphere, and a lot of that material came back down as tiny glassy beads. Geologists call those beads spherules. They rained back through the sky, glowing hot, and as billions of them re-entered the air all at once, they turned the upper atmosphere into something like the inside of an oven. Forests thousands of miles from the crater are thought to have caught fire from the heat coming down out of the sky, not from any flame spreading across the ground. So the first act was fire. Then came the water. The impact was in the sea, so it shoved the ocean aside in a wave that some models put at over a mile high near the crater. That wave rolled out across the Gulf, sloshed up against the coastlines of what's now North America, and in places it appears to have run back and forth, dragging debris in and out like a bathtub that got kicked. You can see the mess it left in the rock. Layers of jumbled sediment that got laid down in hours instead of the usual thousands of years. And then came the long part, which is the part that actually did most of the killing. All that dust and soot and vaporized rock stayed up in the atmosphere, wrapped around the whole planet, and blocked the sun, not for a day, for months, maybe years. Photosynthesis, the process plants use to turn sunlight into food, basically shut down because you can't run on sunlight that isn't reaching the ground. So the plants died back first, then the animals that ate the plants, then the animals that ate those animals. The whole food chain came apart from the bottom, quietly, over a stretch of cold and dark that scientists call an impact winter. Here's how we even know any of this happened, because for a long time nobody did. Back in 1980, a physicist named Luis Alvarez and his son, the geologist Walter Alvarez, were studying a thin layer of clay that shows up in the rock record all over the world, sitting right at the boundary between the age of dinosaurs and everything after. And they found something odd in it. The clay was loaded with iridium, a metal that's rare in the Earth's crust, but common in asteroids. There was far more of it in that one thin band than there had any business being. So their idea, which sounded a little wild at the time, was that the iridium came from space, from a single giant impact, and that whatever hit was big enough to end the dinosaurs. A lot of geologists weren't buying it. The problem was simple. If a rock that size hit the planet, where was the crater? The crater turned up about a decade later, and it had been hiding in plain sight. Oil company geologists surveying the Yucatan had already mapped a strange buried ring structure under the peninsula and the sea just off it, without knowing what they were looking at. When scientists went back and lined it up with the age of that iridium layer, the dates matched. The crater was more than 100 miles across, buried under half a mile of younger rock, centered near that town of Chicxulub. That thin iridium clay, by the way, is the line that separates the Cretaceous period from everything that came after. Geologists call it the KPG boundary. and you can walk up to it in a road cut in Italy or a cliff in New Zealand and put your finger on it. A dark band, a few centimeters thick, with a whole world of animals below it that don't appear above it. Around 3/4 of the species on Earth are estimated to have vanished in the aftermath. The big non-avian dinosaurs, the flying reptiles, those coiled ammonites, the giant marine reptiles, all gone. What made it through tended to be small and able to burrow or hide or scrape by on seeds and dead matter while the sun was out. The little mammals that had been living in the shadows of the dinosaurs for over 100 million years were among the things that survived, and with the giants cleared out, they had room to grow into the gaps. More recently, there's a fossil site in North Dakota called Tanis that seems to capture the day itself. The animals there are buried in a surge of sediment loaded with those glassy impact spherules, and some of the fish at the site have spherules lodged in their gills, as if they breathed in the falling debris while they were still alive. Researchers have even used the position of those beads to argue the impact happened in spring. The crater has a name that fits it now, since Chicxulub in the local Maya language is often translated as something close to Tail of the Devil. Number 2. The Great Dying. 252 million years ago, you could walk from the North Pole to the South Pole without ever crossing an ocean. The planet's land masses sat locked together into a single supercontinent called Pangaea. A single landmass creates a single unbroken global ocean, which geologists call Panthalassa. The interior of Pangaea was a vast dry desert, and the coastlines and river valleys held dense forests of giant ferns and seed ferns. The animals walking through those forests were synapsids, early ancestors of mammals. Gorgonopsians hunted herds of thick-skinned herbivores. They were predators built heavily, blending the frame of a wolf with the scales and posture of a monitor lizard, carrying elongated saber teeth. In the oceans, coral reefs stretched for thousands of miles. The reefs sheltered trilobites, sea scorpions, and heavy-shelled mollusks. It was a crowded, highly specialized global ecosystem. The ground in what is now northern Russia simply tore open. This was a fissure eruption. A crack in the Earth's crust unzips for dozens of miles, and magma pours out continuously, like water overflowing a long trough. Geologists call the resulting volcanic rock province the Siberian Traps. The magma kept flowing, day and night, for roughly 2 million years. It eventually covered roughly 2 million square miles. You could take that much lava and bury the entire United States under rock up to a mile deep. The lava burned the land it touched. The lethal mechanism was what the magma hit on its way up to the surface. Before reaching the air, the rising rock passed through the Tunguska Basin, one of the largest underground deposits of coal and limestone on the planet. The magma baked the coal seams deep underground, igniting them. It became the largest fossil fuel burning event in Earth's history, running continuously for hundreds of thousands of years. Billions of tons of carbon dioxide and methane vented straight into the atmosphere, alongside microscopic ash and toxic heavy metals like mercury. The mercury rained down across the globe, settling into the sediment, where it still registers in the rock record today as a chemical marker of the disaster. The greenhouse effect trapped the sun's heat. Global average temperatures spiked by around 18 degrees Fahrenheit. The planet locked into a fever. On land, the heat wave baked the soil. The global weather patterns shifted, drying the coastal forests into arid wastelands. The plants died back, stripping the soil of the root systems that held it together. The loose dirt simply washed away into the sea. The oceans absorbed the brunt of the disaster. Seawater soaked up massive amounts of that airborne carbon dioxide, acting like a giant chemical sponge. Water holding too much, CO2, turns acidic. The acid eats away at calcium carbonate, the exact material marine animals use to build their shells. The coral reefs slowly dissolved. The microscopic plankton at the base of the food web died off, starving the larger fish. The water stopped moving entirely. Ocean circulation relies on a temperature gradient. Cold, dense water freezes at the poles, leaving the salt behind. That heavy, salty water sinks to the ocean floor, driving a deep-water conveyor belt that pushes currents around the globe. As the world warmed, the polar ice caps vanished completely. The temperature difference between the equator and the poles flattened out. The conveyor belt stalled. The global ocean turned into a stagnant pond. Oxygen from the surface stopped mixing into the deep water. The oceans became anoxic, completely starved of oxygen. Bacteria adapted to oxygen-free environments took over the sea floor. Purple sulfur bacteria multiplied across the globe. These microbes produce hydrogen sulfide as a waste product. The hydrogen sulfide built up in the stagnant deep water until it reached a saturation point, bubbled up to the surface, and vented into the atmosphere. Hydrogen sulfide smells like rotting eggs. It is highly toxic to oxygen-breathing animals, poisoning the nervous system. The gas drifted over the coastlines, choking out the remaining plant and animal life that had survived the heat. Geologists call it the end Permian mass extinction. The numbers mark it as the closest life on Earth has ever come to being completely eradicated. Roughly 90% of all marine species vanished. On land, 70% of vertebrate species died out. The trilobites had survived for nearly 300 million years through multiple earlier planetary catastrophes. The acid and the toxic gas wiped them out entirely. The evidence for this chain of events sits in the rock record, starting with the Siberian lava fields. The stepped basalt hills of the Siberian traps still cover northern Russia. Geologists date those rocks, and the ages match the extinction boundary perfectly. Scientists track the ancient atmosphere by measuring the ratio of carbon isotopes trapped in the sediment. Plants prefer a lighter version of carbon. When millions of tons of coal burned, all that light plant carbon flooded the atmosphere. The rock layers directly on the boundary line show a massive sudden spike in light carbon. The fossil record itself looks like a wall. Below the Permian boundary line, the rocks are packed with diverse shells, bones, and leaf imprints. Above the line, there is almost nothing. Right at the boundary, scientists find a thin band of sediment called the fungal spike. It is packed almost entirely with fossilized fungal spores. For a brief geological window, the most abundant life forms on Earth were the mushrooms and fungi feeding on the rotting forests. Above the fungal spike sits a 10 million year stretch of rock called the coal gap. Geologists find no coal seams anywhere on Earth from this section of the Triassic period. There were no forests left to die and compress into peat. The recovery of the planet took roughly 10 million years. The land was so empty that a single animal expanded to occupy almost the entire terrestrial globe. It was a pig-sized, tusked reptile called Lystrosaurus. It carried a barrel chest, adapted for pulling in the oxygen-poor air, and short, sturdy limbs meant for digging. The environment was relentlessly hot and dry, so Lystrosaurus survived by burrowing deep into the dirt to escape the daytime heat. The downward-pointing tusks let it scrape up dead root matter and whatever hardy fungal growth it could find in the soil. The strategy worked perfectly for the ruined world. If you dig into early Triassic rock layers in South Africa, India, Antarctica, or China, Lystrosaurus bones make up over 90% of all the terrestrial animal fossils you will find. Number 3. The snowball Earth. Look at the Earth from space roughly 700 million years ago, and you would see a featureless white billiard ball. Sheets of ice up to a mile thick sealed the oceans. Glaciers buried the continents under millions of tons of frozen water. The frost stretched from the poles down to the equator, wrapping the entire globe in a continuous, unbroken shell. The surface temperature hovered around -50 degrees Fahrenheit. The planet sat locked in a deep freeze that lasted for tens of millions of years. This was the Cryogenian period. The continents were clustered together in a single giant landmass near the equator, a supercontinent geologists call Rodinia. The land was entirely bare rock. The wind blew over empty plains of granite and basalt. The only life on the planet lived in the water, mostly single-celled microbes and bacterial mats hugging the shallow coastlines. They sat directly in the path of the approaching ice. The freeze started with the breakup of that supercontinent. Tectonic forces began tearing Rodinia apart, ripping open new coastlines and exposing massive amounts of fresh volcanic rock to the elements. Rain mixed with carbon dioxide in the air to form a mild acid, which washed over the fresh stone. The chemical reaction pulled the carbon dioxide out of the atmosphere and locked it into the crust as carbonate minerals. The sky steadily lost its greenhouse gases. The global temperature dropped, and the polar ice caps started creeping south. This triggered a runaway cycle based on the albedo effect. Ice is white, reflecting sunlight back into space. Open ocean is dark, absorbing sunlight and holding warmth. As the glaciers advanced out of the poles, they covered more of the dark water. The planet reflected more heat away, causing the temperature to drop further, which made the ice grow faster. The planet's climate operates like a thermostat, and the shrinking oceans jammed it down. The ice marched steadily toward the equator. Once the glaciers crossed a tipping point around 30 degrees of latitude, the remaining open ocean couldn't absorb enough heat to hold them back. The ice sheets met in the middle. The ocean's surface froze solid. The Earth became a giant orbital mirror. Once a planet freezes that completely, the ice reflects too much solar radiation for the sun to ever thaw it. The Earth sat trapped in this state for roughly 50 million years. The microbes survive by clinging to hydrothermal vents on the pitch-black seafloor, feeding on chemicals bubbling up from the Earth's mantle. The mechanism that finally broke the ice came from deep underground. Heat from the planet's core kept the tectonic plates moving. Volcanoes still erupted, punching holes through the mile-thick ice sheets to spew lava and ash into the freezing air. Volcanoes pump out carbon dioxide. On a functioning Earth, the water cycle manages this gas. Rain washes it out of the sky and flushes it into the ocean, but a completely frozen planet has no liquid surface water to evaporate. The water cycle had shut down. There was no rain. The carbon dioxide poured out of the volcanic vents and accumulated in the atmosphere, century after century. The gas slowly built an invisible blanket around the ice. After millions of years, the concentration of carbon dioxide in the air reached hundreds of times the modern level. The trapped heat finally overpowered the reflection of the ice. The melt started at the equator. Puddles of dark meltwater formed on the ice, absorbing the sun's rays and accelerating the warming. The thermostat jammed in the opposite direction. The ice fractured, exposing the dark ocean underneath, which pulled in massive amounts of heat. The Earth transitioned from a deep freeze into a sweltering hothouse over a geological blink. Super hurricanes battered the remaining ice as the hyperheated atmosphere churned over the freezing oceans. Geologists reconstruct this violent cycle by reading the debris left behind in the rock. Glaciers act like continental bulldozers. As they grind over the land, they pick up boulders and drag them out to sea inside the ice. When the ice melts, it drops those boulders into the fine, powdery mud on the seafloor. Geologists call these misplaced rocks dropstones. You can find them embedded in perfectly flat layers of marine shale, a heavy stone sitting in delicate mud, serving as a clear footprint of moving ice. In the late 20th century, geologists began finding these dropstones in ancient rock formations in Australia, Namibia, and Death Valley. They needed to know where those landmasses were located when the ice dropped the stones. When volcanic rock forms, iron particles inside it align with the Earth's magnetic field, acting like tiny compass needles that freeze in place. By reading the magnetic alignment of the minerals around the dropstones, scientists determined the exact latitude of the mud when it was laid down. The rocks containing the glacial dropstones had been sitting directly on the ancient equator. A planetary scientist named Joseph Kirschvink looked at this tropical glacial evidence in 1992 and coined the term snowball Earth. He laid out the mechanics of the runaway albedo freeze and the unwashed volcanic carbon thaw, explaining exactly how a glacier could drop a boulder into the warmest sea on the planet. The catastrophic melt flooded the oceans with crushed rock. The glaciers had spent 50 million years grinding the continents into dust. and the thaw flushed all that mineral-rich sediment directly into the water. The surviving microbes suddenly found themselves in a warm ocean loaded with nutrients. The oxygen levels in the water spiked as photosynthetic bacteria bloomed in the sunlight. The fossil record, sitting directly above the snowball earth rock layers, shows a sudden shift. Soft, quilted organisms and early sponges appear in the sediment, filtering the mineral-heavy water. Complex multicellular life took hold in the aftermath of the thaw. The physical record of the deep freeze remains locked in the strata. In the Namibian desert today, you can walk up to a dry cliff face and touch a boulder dropped by a glacier into a tropical sea 700 million years ago. Number 4. The Cambrian explosion. Before the Cambrian period, the Earth's oceans were quiet. The seafloor was covered in thick, stable mats of microbial slime. The few larger animals that existed were soft, quilted things shaped like fronds or ribbed discs. They anchored themselves to the mud and absorbed nutrients directly from the water. They possessed no mouths, no digestive tracts, and no eyes. It was a static ecosystem, drifting unchanged for tens of millions of years. Around 540 million years ago, the chemistry of the oceans shifted. Glaciers from a previous ice age melted, and weathering stripped calcium and other minerals off the continents, washing them into the sea. That influx of minerals provided the raw building material for animals to construct hard shells and armor plating. The sudden arrival of biological armor triggered the Cambrian explosion. The word explosion is a relative term in deep time. The event stretched over roughly 20 to 25 million years, which is a slow crawl to a human, but a sudden flash in the lifespan of a planet. It functioned essentially as an open workshop for evolution, a period of rapidly testing body plans to see what survived. The quiet sea floor was ripped apart by burrowing worms. Animals started swimming freely in the water column, grazing away the microbial mats. And with mobility came the need to see where you were going. The Cambrian period saw the development of the first true eyes. Lenses made of solid calcite crystal formed in the heads of early marine arthropods called trilobites, allowing them to track movement in the water. So once one animal could see and move, it could hunt. The ocean settled into a biological arms race. Prey species developed spines, thick armor, and chemical defenses to survive. Predators adapted with compound eyes, swimming fins, and crushing jaws to overcome those defenses. The basic architecture for almost every major animal group alive today was established in this narrow geological window. The ancestors of insects, mollusks, and vertebrates all appear in the rock record here, locked in their first recognizable forms. To understand exactly how these early animals functioned, researchers needed more than just scattered shells. They needed a snapshot of the whole organism, including the soft tissue. Charles Walcott found that snapshot. He was the head of the Smithsonian Institution, an experienced field geologist who spent his summers combing the mountains of British Columbia for early life. In August of 1909, Walcott was riding a horse along a high mountain pass near a ridge in the Canadian Rockies. According to his notes, he spotted a loose block of dark shale containing silver-colored fossil shapes. He tracked the loose blocks up the steep slope to their source, a band of rock he named the Phyllopod Bed, which later became known as the Burgess Shale. Over the next 15 years, Walcott and his family quarried a massive trench into the side of the mountain. They shipped over 60,000 specimens back to Washington, splitting the shale plates open to reveal a perfectly preserved ecosystem. The reason the Burgess Shale fossils are so detailed comes down to a geological accident. During the Cambrian, this part of Canada sat near the equator, submerged beneath a shallow tropical sea. The seafloor ended in a steep underwater cliff. Earthquakes periodically shook mud loose from the top of the cliff, triggering underwater avalanches that swept the animals living there down into the deep, oxygen-starved water below. The fine mud entombed them instantly. The lack of oxygen stopped bacteria from breaking down the soft tissues, preventing the animals from rotting. The mud eventually compressed into a dark rock called shale, pressing the animals flat like flowers in a heavy book. It captured the exact impressions of gills, digestive tracts, and eyes. When paleobiologists began examining Walcott's fossils decades later, they had to invent entirely new categories to classify them. The creatures pulled from the rock looked like they belonged on another planet. Anomalocaris was the apex predator of this new ocean. Its name translates to abnormal shrimp. Researchers initially found its fossilized feeding appendages isolated from the rest of the body, classifying them as actual headless shrimp. They uncovered its circular crushing mouthparts in a different rock layer and logged them as fossilized jellyfish. Paleontologists eventually realized they were looking at the scattered pieces of one massive meter-long hunter. It swam by, undulating a series of overlapping lobes running down its sides, sweeping the water for trilobites. It possessed two large compound eyes sitting on stalks, giving it a wide view of the seafloor. It grabbed prey using a pair of spiked feeding appendages near its mouth, feeding them into a circular disc of crushing plates. Opabinia was a much smaller creature, only a couple of inches long. It swam near the seafloor using its own set of overlapping flaps, steering with a fan-shaped tail. It carried 5 compound eyes clustered on the top of its head. A hollow, flexible trunk extended forward from its face like a fire hose, ending in a grasping claw lined with spines. It used that claw to pluck soft worms out of the mud and fold them back to a mouth located under its head. Then there was Hallucigenia, a worm-like animal that baffled scientists for decades. It carried 7 pairs of stiff spines on one side of its body and a row of soft tentacles on the other. Researchers initially reconstructed the animal upside down, assuming the stiff spines were legs for walking in the mud. It was, at minimum, an inefficient way to move. They eventually flipped the model over, placing the soft tentacles on the ground and the spines pointing upward as a defense mechanism. Another predator in the shale, named Wiwaxia, looked like a small armored dome. It was covered in flat, overlapping carbonaceous scales, with 2 rows of tall, vertical spines sticking up from its back to deter anything trying to swallow it whole. It dragged itself along the seafloor, scraping up organic matter with a specialized feeding structure equipped with 2 rows of teeth. Among these bizarre predators and heavily armored bottom feeders lived a tiny, unremarkable creature named Pikaia. It was about 1.5 inches long, shaped like a flattened eel, and covered in soft skin. It swam by flexing its body side to side. Pikaia is one of the earliest known chordates, the broad group of animals that includes all modern fish, amphibians, reptiles, and mammals. The fossil shows a stiff rod of cartilage running down the length of its back, supporting a simple nerve cord. Every vertebrate alive today traces its basic architecture back to something very much like that inch-long ribbon, flexing a set of V-shaped muscles to navigate the dark mud of a newly dangerous ocean. Number 5. The Toba Super Eruption. Sumatra, roughly 74,000 years ago, had a mountain that spent weeks turning itself inside out until it became a lake. Deep underground, a reservoir of magma had been expanding, pushing up against the crust, fracturing the rock above it. When the pressure finally broke the seal, the mountain collapsed into its own empty magma chamber. The ground gave way, leaving a hole 100 kilometers long. Water eventually filled the crater. Today, we call that hole Lake Toba. It sits in Indonesia, a massive blue caldera holding an island in its center. The collapse of that mountain was one of the largest volcanic eruptions of the last couple of million years. Volcanic explosions are measured on a specific index that tracks the sheer volume of material ejected. That scale maxes out at 8. Toba was an 8. The mechanics of an eruption that size reshaped the immediate geography. A caldera collapse is a sinkhole on a tectonic scale. The magma evacuates the chamber. The ceiling loses its support, and millions of tons of rock drop straight down. That action forces whatever is left inside the volcano straight up into the stratosphere. The volcano threw thousands of cubic kilometers of rock, pumice, and ash into the sky. High-altitude winds caught that ash and dragged it west. It blew across the Indian Ocean, burying the Indian subcontinent and parts of the seafloor under a gray blanket. In some places, that layer built up to 6 meters deep. Volcanic ash is made of microscopic shards of glass and shattered rock. It coats the leaves of plants, it clogs the gills of fish, and it collapses the roofs of any shelters built beneath it. Marine sediment cores, pulled from the bottom of the Indian Ocean, show the exact same fallout. The ash settled on the water, sank through the dark, and formed a thick sludge on the seafloor. Along with the ash came sulfur dioxide. When sulfur dioxide hits the stratosphere, it reacts with water vapor to form aerosols. Those aerosols act as a planetary sunshade, reflecting incoming sunlight back into space. The result is a volcanic winter. Temperatures drop globally. The planet gets cold and stays that way until the chemical aerosols eventually settle out of the atmosphere over years or decades. Early human populations were living through this chill, scattered across Africa and Asia. Decades later, scientists mapping modern human DNA noticed a severe narrowing in our ancestry. Genetic diversity in modern humans is unusually low. A genetic bottleneck is a funnel. You pour a diverse, widely spread population in the top. Only a few individuals squeeze through the narrow neck to start the population over on the other side. Everyone alive today carries the DNA of just those few survivors. The timing of that genetic squeeze aligned roughly with the crater in Sumatra. An anthropologist named Stanley Ambrose studied that timeline and connected the genetic data to the volcano. He proposed the Toba catastrophe theory. His argument was that the supereruption triggered a decade-long volcanic winter, followed by a 1,000-year cooling phase. That deep freeze nearly wiped out early humans, forcing a few thousand survivors into isolated, warmer pockets in Africa. It provided a clean explanation for the genetic data. The volcano erupted, the world froze, and humanity barely scraped by. Other researchers started digging into the dirt to test the theory. They looked for the breaks in the archaeological record, the empty spaces in the soil where human tools should have disappeared during the long freeze. They found something else entirely. In places like southern India, where the ash fell thickest, archaeologists uncovered stone tools sitting right below the Toba ash layer. They kept digging into the dirt right above the ash layer. They found the same style of stone tools sitting there too. The people living there survived the eruption and just kept making the exact same equipment. Some climate models run by later researchers suggested the cooling effect was shorter and less severe than Ambrose originally thought. The models point to a regional disaster over South Asia. The human genetic bottleneck definitely happened, and the dates are wide. Many scientists now attribute the bottleneck to shifting climates or slow migrations spanning tens of thousands of years. The debate keeps going, mostly because pinning a genetic squeeze to a single exact date in the rock record is tough work. We know the exact scale of the eruption itself because the chemical debris never went away. Glaciologists drilling deep ice cores in Greenland and Antarctica use hollow bits to pull up cylinders of ancient ice that preserve the atmosphere year by year. Right around 74,000 years ago, the ice captures a massive spike in sulfur. The sulfuric acid from the eruption rained down on the poles and froze into the ice sheet, leaving a chemical scar you can point to. And then there is the ash itself. You can go to the Jwalapuram archaeological site in India, grab a trowel, and dig down into the soil. You will hit a band of pale, fine volcanic glass, lying exactly where it fell when the sky turned gray. Number 6. The Zanclean Flood. 5.3 million years ago, the Mediterranean Sea was gone. The entire basin from the coast of modern-day Spain all the way across to Syria was a dry, salt-crusted sinkhole. It plunged thousands of feet below global sea level. Rivers flowing down from Europe and Africa bypassed the old coastlines and carved deep, jagged canyons into a barren white plain, emptying into scattered hypersaline lakes that were too toxic for most life to handle. Down at the bottom of the basin, the air pressure was heavy, thick and brutally hot. This was the end of the Messinian salinity crisis. The Atlantic Ocean was about to break back in. About 600,000 years earlier, the African and Eurasian tectonic plates had drifted into each other just enough to pinch off the Strait of Gibraltar. The Mediterranean is essentially a giant evaporation pan. It loses far more water to the sun than it ever gains from rain or rivers, so it relies entirely on a steady current from the Atlantic to keep it topped off. Once that rocky land bridge lifted out of the sea and choked off the connection, the water simply baked away. It left behind an incredible amount of salt. When a sea evaporates, the minerals dissolved in it precipitate out and coat the floor. In the 1970s, a deep-sea drilling ship called the Glomar Challenger sank hollow pipes into the Mediterranean seabed and pulled up cores of solid crystalline salt. In some places, that salt layer is a mile thick. The whole sea had turned into an empty, white-crusted oven. The rivers that used to feed the sea had to adjust to this new reality. Because the base level of the ocean had dropped by a couple of miles, rivers like the Rhone in France and the Nile in Egypt suddenly found themselves flowing off the edge of a massive cliff. Over hundreds of thousands of years, they carved sheer, enormous gorges down into the continental shelf, trying to reach the bottom of the empty basin. The ancient Nile carved a canyon thousands of feet deep that stretched hundreds of miles inland, right under where the city of Cairo sits today. Then the earth shifted again. The land bridge at Gibraltar began to subside, settling just low enough for the Atlantic Ocean to start lapping over the top of the rock. It started as a trickle. A small spill of seawater found a low point in the natural dam and ran down the miles-long slope into the dry basin. Water cutting through rock operates on a vicious feedback loop. A small channel allows a little water through. That water scours away some of the rock, which makes the channel deeper, which lets more water through, which carves the rock away faster. Geologists call what happened next the Zanclean Flood. The trickle turned into a torrent, and the torrent unzipped the bedrock. Think of it like a dam failure, but on a planetary scale, or an emptied bathtub refilling through a crack in the side that suddenly gives way all at once. Once the Atlantic punched a proper hole through the Strait of Gibraltar, it sheared the rock apart. The water shot down a ramp of exposed stone, dropping more than a mile in elevation. Models of the event suggest the floodwaters tore through the gap at speeds topping 90 miles an hour. It was a chaotic wall of water, mud, and shredded bedrock scouring across the salt flats. At its peak, the flow rate is estimated to have been roughly 1,000 times greater than the discharge of the Amazon River. The entire basin, a geographic depression large enough to hold multiple modern countries, refilled in just a few years. Some estimates put the timeline at less than a year, with the water level inside the basin rising by more than 30 feet a day during the height of the surge. The massive river canyons carved by the Nile and the Rhone were suddenly swamped, turning into deep, saltwater estuaries that slowly filled in with sediment over the next few million years. Any sparse life that had adapted to the deep, salty desert was instantly buried under a wall of deep blue Atlantic water. The evidence for this sits quietly in the rock record. When geologists look at the core samples pulled from the Mediterranean floor, they see a harsh, sudden line. There is a thick layer of desert salt and gypsum, and sitting directly on top of it is deep-sea mud packed with the microscopic shells of open ocean plankton. The layers touch directly, jumping from desert salt to deep ocean mud in a single line. The environment switched from a dry basin to a deep ocean virtually overnight in geological time. Marine animals from the Atlantic simply swam back into a sea that had been a desert a decade earlier. Researchers eventually mapped the sea floor at the Strait of Gibraltar using seismic reflection profiling, bouncing sound waves deep into the crust to see the shapes of the buried rock layers beneath the modern sand and mud. They found an ancient U-shaped channel nearly 200 miles long, buried under younger sediment. It cuts directly through the strait, sloping downward from the Atlantic shelf into the Mediterranean deep. The channel is scoured smooth, carved out by the water that tore the land apart to put the ocean back. Number 7. The Great Oxidation event. Roughly 2.4 billion years ago, the Earth had an orange sky and a green ocean. The air was a thick atmospheric haze of methane, carbon dioxide, and water vapor. There was no free oxygen. The planet was populated entirely by single-celled microbes drifting in the shallow seas and clustering around deep hydrothermal vents. They pulled their energy from sulfur, iron, and the ambient heat of the crust. They thrived in an environment that would kill any modern animal in minutes. This is the Great Oxidation Event. It was the planet's first global pollution crisis, and it permanently poisoned the existing biosphere. The perpetrators were cyanobacteria. These were microscopic, blue-green organisms floating in the coastal waters, and they developed a mechanical advantage over their neighbors. They figured out how to use sunlight to synthesize food. Photosynthesis works by taking in water and carbon dioxide, using solar energy to split the molecules apart, and building sugars out of the carbon and hydrogen. The cyanobacteria kept the fuel they built and discarded the leftover oxygen, venting it directly into the water around them as waste. They multiplied. They formed dense, sticky mats across the continental shelves, absorbing sunlight and pumping out microscopic bubbles of oxygen day and night. Free oxygen is a highly reactive gas. It stabilizes itself by stealing electrons from other elements. For the existing anaerobic microbes that had evolved over 1 billion years in an oxygen-free world, this new waste gas was lethal. An environment flooding with oxygen was like a room flooding with vaporized bleach. The gas stripped electrons from their organic structures, tearing their cell walls apart from the outside in. The mass die-off didn't happen immediately because the Earth had a built-in chemical sponge. The ancient green oceans were saturated with dissolved iron. As the cyanobacteria released oxygen, the gas immediately collided with the iron in the water. The two elements bonded, creating iron oxide. The ocean was literally rusting from the inside out. Billions of tons of solid iron oxide flakes precipitated out of the water column and rained down onto the seafloor. They settled in the mud, trapping the toxic oxygen at the bottom of the sea and keeping the upper waters safe for the older microbes. The cyanobacteria would bloom, the ocean would rust, and a layer of red iron would coat the seabed. Then the algae would die back, and a layer of gray silica would settle over the rust. This cycle ran on a quiet, slow loop for hundreds of millions of years. Then the ocean ran out of iron. With the dissolved iron used up, there was nothing left to capture the waste gas. Free oxygen began building up in the water column. It saturated the coastal seas, burned through the surface microbes, and then bubbled up into the orange sky. Once the oxygen hit the atmosphere, it triggered a climate collapse. The planet's warmth had been maintained by a thick blanket of methane gas. Oxygen reacts violently with methane, converting it into carbon dioxide and water. Carbon dioxide traps heat, but it is far weaker than methane. So as the oxygen scrubbed the methane out of the sky, the planetary thermostat plummeted. The Earth froze into the Huronian glaciation. Ice sheets advanced from the poles all the way down to the equator, locking the planet in a deep freeze that lasted for up to 300 million years. Geologists find glacial dropstones, heavy boulders carried out to sea by icebergs and dropped into the mud, sitting in rock layers that formed near the ancient equator. The entire globe became a snowball. Underneath the ice, the oxygen concentration just kept rising. The older microbes were eradicated from the open ocean. The survivors retreated into the deep mud, the ocean trenches, and the oxygen-starved dead zones near underwater volcanoes. They hid in the dark, and their descendants still live in those exact anaerobic pockets today. The oxygen built up to a point where it formed the ozone layer, blocking ultraviolet radiation and allowing life to eventually migrate out of the deep water. Some organisms mutated to survive the oxygen. A few eventually mutated to harness its reactive power for energy, becoming the ancestors of all complex, oxygen-breathing life. We track the timeline of this shift using the rocks left behind on the seabed. Geologists locate the exact millennia the ocean filled with oxygen by mapping out banded iron formations. These are massive deposits of sedimentary rock, striped with alternating bands of dark red iron oxide and gray silica. They are the fossilized rust from the Great Oxidation Event, pressed into stone. When a mining company blows the top off a mountain in the Pilbara region of Australia, they are digging into this exact timeline. You can walk up to these exposed formations in Western Australia, northern Michigan, and South Africa. The red layers sit there in the rock face, hundreds of feet thick, recording the centuries when the iron soaked up the poison. The vast majority of the iron ore mined for modern industry comes from these specific bands. The steel girders inside modern skyscrapers are forged directly from the rusted chemical waste of Precambrian bacteria. The rock layers abruptly stop recording that red rust roughly 2 billion years ago. That solid gray line in the strata marks the exact point. The ocean exhausted its iron buffer and the planet filled with toxic air. Number 8. The Permian coal forests collapse. Picture a swamp stretching across the equator of an ancient supercontinent, roughly 305 million years ago. The air is thick with humidity and buzzing with giant insects. The trees growing out of the muck are scale trees, primarily a genus called Lepidodendron, towering 100 feet into the air. They have no branches until the very top, and their pale green trunks are textured with diamond-shaped patterns that look like tire treads. Dead trunks lie stacked in stagnant, oxygen-starved water. It is a quiet, wet, unending green world. This was the Carboniferous rainforest. It covered much of the planet's landmass until the global climate fractured it into pieces. The Earth was in the middle of pulling its continents together to form the supercontinent Pangaea. Right across the middle, the tropical belt held a continuous forest spanning thousands of miles. The plants had recently evolved a tough new structural polymer called lignin, which allowed them to grow tall and build sturdy trunks. White rot fungi, the organisms that break down wood today, evolved millions of years later. When these massive trees fell into the swamp, they stayed intact. Their shallow root systems meant they fell over constantly. They piled up in the mud, layer upon layer, for millions of years. The animals thriving in this damp environment were giant amphibians. They grew to the size of crocodiles and ruled the muddy banks as apex predators. They depended on the constant moisture to keep their skin from drying out and to lay their jelly-like eggs directly in the water. The whole ecosystem was tethered to that unending humidity. The forest effectively engineered its own destruction. By trapping all that plant matter in the swamp mud and burying it, the forest pulled massive amounts of carbon dioxide out of the atmosphere. Removing that greenhouse gas triggered a global cooling effect. Ice started building up at the South Pole. Glaciers expanded across the southern land masses, locking up the planet's liquid water and solid ice. Sea levels dropped. The global rainfall patterns shifted drastically. The endless damp equatorial climate broke apart. The continuous belt of rainforest tore into smaller, isolated patches of green, surrounded by vast stretches of dry, arid scrubland. Think of a sprawling lake slowly drying up in a drought. The single large body of water separates into a chain of smaller ponds and eventually just scattered puddles. The rainforest did exactly that. The continuous habitat broke into shrinking islands of moisture separated by expanding deserts. For the giant-scale trees and the amphibians, those islands were a trap. The plants needed water to reproduce, casting their spores into the damp soil. As the dry gaps between the forest patches widened, the species living in one patch could no longer mix with the species in the next. The giant amphibians were stranded on these shrinking green rafts. This isolation caused a brief burst of new species, as the separated populations adapted to their specific puddles. When a local patch of forest finally dried out completely, everything living in it died. The massive club mosses simply couldn't survive the dry dirt, and their towering forests collapsed. New life took over the arid gaps. Plants that had evolved seeds with protective hardcoats could wait out the dry spells, so early conifers and seed ferns spread across the plains. The animals shifted right alongside them. Reptiles had a distinct advantage over amphibians because they laid amniotic eggs with leathery shells that held moisture inside. The egg acted like a portable pond. A reptile could walk straight out into the dry sand, lay its eggs, and leave the swamp behind. The fracture of the rainforest handed the terrestrial world over to the reptiles. Geologists read this entire collapse directly in the rock layers. The boundary is marked by a massive visual and chemical shift. Below the boundary, the rocks are dark, carbon-rich black shales, packed with the fossilized spores of moisture-loving swamp ferns. Above the line, those spores vanish, replaced entirely by the pollen of drought-resistant seed plants. The rock itself changes color, shifting into red beds. These are oxidized sandstones, essentially mud, that dried out and rusted in the open air. You can see the physical remnants of the trees themselves at places like the Joggins Fossil Cliffs in Nova Scotia, where fossilized stumps still stand upright in the coastal rock, exactly where they grew and died. The millions of years of fallen scale trees that piled up in the stagnant water before the drying stayed exactly where they fell. They were buried under sediment, heated, and compressed by the weight of the rock above them. Those buried layers of ancient swamp are the coal seams we pull out of the earth today. Number 9. The Azolla Event. 49 million years ago, the North Pole looked like a Louisiana bayou. The water was warm, sitting roughly at the temperature of a modern swimming pool. Crocodiles hunted along the coasts of what is now Greenland. Palm trees grew on the shorelines. Early primates and turtles lived in forests near the top of the world, and floating on the surface of that warm, still ocean was a blanket of green. It was a tiny freshwater fern called Azolla, and it stretched across the water in a mat the size of a continent. This is the Azolla Event. It forced a hothouse planet into an ice age using dead leaves. During the Eocene epoch, Earth was trapped in a severe greenhouse state. Atmospheric carbon dioxide levels sat dangerously high, at least triple what they are today, trapping solar radiation and baking the globe. The poles were completely bare of ice. The geography of the planet was shifting, and the Arctic basin was surrounded by land. North America, Greenland, and Eurasia formed a tight ring around the pole, leaving only narrow, shallow channels connecting the Arctic to the Atlantic and Pacific Oceans. It functioned as a giant, warm, stagnant lake. Heavy global rains washed massive amounts of fresh water off the surrounding continents and dumped it into the basin. Because fresh water is lighter than salt water, it floated. It formed a distinct lid over the denser ocean water below. That stratification created a perfectly still, nutrient-rich surface layer, bathed in 24-hour summer sunlight. Azolla thrives in exactly those conditions. It is a floating plant about the size of a thumbnail. Today, rice farmers in Asia grow it in their paddies to fertilize the soil. It possesses a symbiotic relationship with a specific type of cyanobacteria housed inside its leaves. The bacteria pull nitrogen directly from the air and feed it to the fern, functioning as a built-in fertilizer factory. Supplied with endless sunlight, fresh water, and its own nitrogen, the plant grows incredibly fast. A patch of Azolla can double its total mass in 3 days, so it bloomed across the entire Arctic basin. As the ferns grew, they pulled carbon dioxide out of the air to build their cell walls and stems. They lived, they reproduced, and they died. When they died, the plants sank through that buoyant freshwater lid, down into the stagnant salt water below. That deep water held zero oxygen. Oxygen drives the bacteria that rot dead plants and release their stored carbon back into the environment. In this oxygen-starved deep zone, decay stopped entirely. The ferns simply piled up in the cold dark, taking their captured carbon with them. The cycle acted as a slow, planetary air scrubber. A fern grew, grabbed a tiny pocket of carbon from the atmosphere, died, and locked it away in the mud. Then another fern immediately took its place on the surface. This loop ran continuously for roughly 800,000 years. Trillions of tiny ferns stacked up on the seafloor, compressing into dense mats. Together, they dragged massive volumes of carbon dioxide out of the Eocene sky. Estimates suggest the firn pulled down enough carbon to drop atmospheric levels from around 3,500 parts per million to under 700. As the atmosphere thinned out, the greenhouse effect weakened. The global temperature steadily dropped. The Earth cooled enough for the first permanent ice sheets to form at the poles, setting up the climate cycles that dictate the modern world. The event ended when shifting tectonic plates finally opened the Arctic basin back up to the Atlantic. Saltwater rushed in, mixing the ocean and disrupting the freshwater lid, and the great fern bloom collapsed. Scientists found the evidence during the 2004 Arctic coring expedition. Drilling into the ocean floor near the North Pole is mechanically brutal because the sea ice constantly moves. A fleet of 3 icebreakers, including a Russian nuclear-powered ship called the Sovietsky Soyuz, had to coordinate their movements to smash incoming ice floes up to 10 feet thick. They drove in circles, fracturing the ice, to protect a central drill ship so it could hold its exact position over the Lomonosov Ridge. That ridge is an underwater mountain range running across the center of the Arctic Ocean. The ship dropped a drill pipe through the water, punched into the seabed, and pulled up long cylinders of sediment dating back tens of millions of years. Mixed into those, ancient mud cores were dark, laminated bands. They were the perfectly preserved, fossilized remains of the Azolla ferns. The core samples show exactly when the fern arrived and when it vanished. The plant is still down there, compressed into a rock layer 26 feet thick, resting quietly beneath the Arctic ice. Number 10. The Storegga Slides. Roughly 8,200 years ago, deep underwater off the coast of what is now Norway, the edge of the continental shelf quietly gave way. Mud and rock had been stacking up there for tens of thousands of years, pushed out to sea by the retreating Ice Age glaciers. The pile eventually got too heavy, and the slope lost its grip. A slab of the seabed detached and began to slide into the deeper water of the Norwegian Sea. This was the start of the Storegga Slides. The amount of material that moved in the largest of these collapses was roughly the size of Iceland. Looking at a map of Northern Europe at the time explains what a slide that massive did. Britain was connected to mainland Europe by a vast, low-lying stretch of marsh, estuary, and woodland known as Doggerland. Mesolithic hunter-gatherers lived across it. They fished the shallow coastal waters, hunted deer, and built seasonal camps in the wetlands. Over the previous few thousand years, melting glaciers had been slowly raising global sea levels, swallowing the edges of Doggerland generation by generation. By 6,200 BC, the land bridge had been reduced to a marshy, sinking peninsula. The people living on it were already running out of high ground. An underwater landslide displaces water differently than an earthquake does. It works essentially like pushing a shovel blade flat through a bathtub. The moving rock shoves the entire water column from the seafloor to the surface. When that Iceland-sized chunk of the Norwegian shelf dropped into the deep ocean basin, it dragged millions of cubic miles of water down with it. The ocean rushed back in to fill the void, and the resulting rebound created a tsunami that rippled out across the North Sea. Out in the deep ocean, the wave would have been a long, fast, barely noticeable swell. As it rolled south and hit the shallowing waters around Britain and Doggerland, the physics changed. The front of the wave dragged on the seafloor and slowed down. The back of the wave kept moving at deep-sea speeds, and the water stacked itself up into a wall. Computer models suggest the wave that hit the Scottish coastline was somewhere around 80 feet high. The wave that hit the remaining lowlands of Doggerland was shorter, and Doggerland lacked any 80-foot hills. The water simply washed entirely over the marshlands. The Mesolithic families living on the coast had no warning system. The water would have suddenly drained away from the shore, exposing miles of seabed before the horizon turned white and brought the ocean back inland at highway speeds. Coastal encampments were submerged in a few minutes. The waves swept through the forests, snapping trees and carrying ocean debris miles inland, before eventually pulling back and dragging whatever it caught out to sea. While the water eventually receded, the sea level was still steadily rising from the global glacial melt. The Storega wave scoured away the remaining low coastal barriers, holding the ocean back from the marshlands. Doggerland was effectively broken, and Britain was permanently severed from the continent, surrounded by open water. The mechanism that caused the slide is still a subject of geological study. The leading explanation is that the retreating ice sheets removed a massive amount of weight from the Earth's crust, causing the land off Norway to rebound upward. That shifting triggered earthquakes, which shook loose the unstable sediment. Another factor likely involved methane hydrates, which are pockets of frozen gas buried under the seabed. As the ocean water warmed after the Ice Age, that frozen gas melted, expanding and destabilizing the mud holding it together. Once one section failed, the rest followed. Marine geologists today map the remains of that event using sonar and deep-sea drilling. The primary scar left behind on the Norwegian continental shelf is nearly 200 miles across. It looks like a massive bite mark in the underwater cliff face, showing exactly where the sediment tore away and fanned out into the abyssal plain. We also have the physical debris the wave left behind on land, which marks its exact reach. Geologists digging trenches in eastern Scotland found an anomaly buried under the soil. Miles inland, sitting far above the modern beach, there is a thick, sudden band of gray ocean sand packed with broken marine shells and microscopic deep-sea algae. The sand sits in a single neat layer between deposits of ordinary dark, terrestrial peat. Number 11. The Late Heavy Bombardment. 4 billion years ago, if you could stand on the cooling crust of the early Earth and look up at the young moon, the sky would have been a steady rain of rock. The solar system had already finished its initial construction phase. The planets had cooled into solid spheres, slowly sweeping their orbits clear of the leftover planetary rubble. The inner solar system had settled into a quiet rhythm. Then, hundreds of millions of years after the planets first formed, the inner solar system was caught in a sudden crossfire. This period is called the Late Heavy Bombardment. It was a massive delayed spike in asteroid strikes that battered Earth, Mars, Venus, and the Moon for millions of years. Massive rocks, some of them tens or hundreds of miles across, slammed into the Earth's crust, boiling away whatever early oceans were trying to pool on the surface. If primitive microbial life had already started to form in the water, the heat of those impacts would have sterilized the surface entirely, forcing anything that survived to hide deep in the crust. The reason this sudden barrage happened usually comes down to the giants in the outer dark. The leading explanation is a mechanism called orbital migration. Jupiter, Saturn, Uranus, and Neptune formed much closer together than where they sit today. They were surrounded by a thick, icy disk of leftover building materials, essentially a massive ring of comets and asteroids. Over time, as the gravity of those giant planets interacted with all that leftover debris, their orbits began to drift. Saturn, Uranus, and Neptune crept slowly outward, pushing into the icy ring, while Jupiter shifted slightly inward. Eventually, the gravity of those shifting giants hit a tipping point. The orbits of Jupiter and Saturn locked into a resonance, meaning they started lining up perfectly as they circled the sun. Every time they aligned, their combined gravity tugged on everything else around them. It worked like a gravitational snowplow. The orbits of the smaller outer planets shifted violently, and that thick ring of icy debris got scattered in all directions. Billions of tons of rock and ice were flung out into deep space, while millions of other massive rocks were hurled straight inward, toward the sun. Earth and the moon just happened to be sitting in the line of fire. Earth took the heaviest portion of this barrage because it has stronger gravity, pulling more of those incoming rocks down into its surface. Today, you will not find a single crater from this era on Earth. Wind, rain, and tectonic plates eventually erased all that early damage, melting the crust back into the mantle and paving over the evidence. The moon kept its scars. It is a geologically dead world, with no atmosphere to burn up incoming debris, no weather to wash away a blast zone, and no shifting plates to swallow one. Whatever hits the lunar surface stays exactly where it landed. When you look up at a full moon today and see those large, dark, circular patches, you're looking directly at the blast zones from the Late Heavy Bombardment. The asteroid impacts were so massive they punched straight through the lunar crust, allowing dark lava to bleed up from the interior and pool in the craters. Those lava pools eventually cooled into the flat, dark plains we see now. We know those craters are exactly that old because of the Apollo missions. When astronauts walked on the moon in the late 1960s and early 1970s, they collected hundreds of pounds of rock and brought it back to Earth. Geologists tested those samples, specifically looking for impact melt. Impact melt is rock that got briefly liquefied by the intense heat of an asteroid strike and then rapidly cooled into glass, locking the exact date of the impact into its chemical structure. Geologists dated those melted rocks to map the history of lunar impacts. The dates clustered cleanly together. Almost all the impact melt the Apollo crews brought back had been created in a tight window, roughly 3.9 billion years ago. That clustered timeline is what first told scientists about the sudden, violent spike in impacts. Researchers still argue over the exact scale of the event. The current debate in planetary science is whether the late heavy bombardment was a massive, sudden spike caused by shifting planets, or simply the tail end of a steady, declining rain of rocks that had been falling since the solar system formed. Some geologists argue the Apollo astronauts just happened to land in areas covered by debris from one single, massive impact basin, skewing the samples to all read the same age. That argument is still playing out in labs today. The timeline itself remains locked in stone. The entire history of that violent window sits quietly in climate-controlled vaults in Houston, inside the glass and melted rock chipped off a dead world. Number 12, the Eltanin impact. About 2.5 million years ago, an asteroid roughly a mile wide fell toward the Southern Ocean between South America and Antarctica. The water there was nearly 3 miles deep, pitching with heavy swells in the freezing dark. When the rock hit the surface, it didn't slow down. It vaporized a column of seawater a mile wide in a fraction of a second, driving a shockwave straight down into the abyssal mud. An impact on land leaves a bowl of melted rock. A deep ocean strike works like a bullet fired straight down into a swimming pool. The water absorbs the sheer kinetic energy, blowing outward to form a massive temporary cavity, and then collapses back in on itself. The rock shattered against the seabed, turning into molten shrapnel. Millions of tons of vaporized ocean and pulverized meteorite blasted upward, punching through the atmosphere and raining back down across the southern hemisphere. Then the ocean rushed back to fill the empty column. The water collided with itself at the center of the impact zone, forcing a liquid pillar miles into the sky. When that pillar collapsed, it triggered a mega tsunami. Waves rolling across the open ocean travel fast and low, but as they approached the coastlines of Antarctica, South America, and New Zealand, the rising continental shelves forced the energy upward. Some modeling suggests the waves hitting the coast of Chile reached over 600 feet tall. Those walls of water ripped up the coastal seafloor, churning marine sand and deep water shells together. They scoured the coastlines down to the bedrock, tore away forests, and dragged salt and ocean debris miles inland. The sheer volume of water vapor and salt thrown into the upper atmosphere likely altered the global climate for years, wrapping the planet in a reflective cloud cover that blocked the sun and dropped temperatures worldwide. But down at the bottom of the ocean, the immediate violence ended quickly. The shattered pieces of the asteroid settled into the mud. They spread out over hundreds of square miles, mixing with the torn-up remains of microscopic sea life. They sat there under 3 miles of freezing water for 2.5 million years. The USNS Eltanin was a military cargo ship converted into an oceanographic research vessel. Throughout the 1960s and 70s, it cruised the waters around Antarctica, acting as a floating laboratory. The scientists on board mapped the ocean currents, studied marine biology, and charted the ocean floor. They regularly used a heavy wire mesh dredge bucket, dropping it over the side on a thick steel cable and letting it scrape along the bottom of the sea. They were pulling up mud, manganese nodules, and rocks to read the geological history of the region. During a survey in the Bellingshausen Sea, they hauled the dredge up from a depth of over 2 miles and dumped the gray mud onto the wet deck. Among the usual deep-sea debris, they found something completely out of place. They had pulled up chunks of metal and melted glassy rock. The fragments were mesositerites, a rare type of meteorite made of roughly equal parts iron, nickel, metal, and silicate rock. They carried the distinct chemical signature of an object from space, packed with high levels of iridium and osmium. The crew had accidentally dredged up the scattered remains of an asteroid. Researchers started looking closer at sediment cores pulled from that exact patch of the ocean. A standard deep-sea core sample looks like a long tube of packed dirt, showing neat, flat layers of dust and dead plankton settling slowly over millions of years. The cores from the El Tannin site showed a chaotic, jumbled mess. The sediment was packed with the smashed shells of diatoms and radiolarians, single-celled plankton that usually drift gently to the bottom when they die. Here their remains were shredded and mixed with chunks of bedrock torn from seamounts hundreds of miles away, along with tiny melted beads of asteroid glass. The bottom of the ocean had been violently scrambled in a single afternoon. Because the asteroid hit deep water, it never carved a permanent crater into the continental crust. It just sterilized a vast stretch of the Pacific and left a layer of cosmic debris scattered across the plain. The impact was entirely hidden from the surface. The only reason anyone knows a mile-wide rock hit the Earth 2.5 million years ago is the handful of meteorite fragments the El Tannin's dredge bucket scraped out of the deep seabed. Number 13. The Younger Dryas. Roughly 12,900 years ago, the Ice Age was ending. The glaciers that had buried North America and Europe under miles of ice were in full retreat. Oak and ash forests were creeping north across the newly exposed soil. Human hunters were following migrating herds of elk and mammoth into river valleys that had been frozen solid for millennia. The planet was warming steadily. Then, within the span of a single human lifetime, the glaciers stopped melting and started advancing again. The cold returned, dropping average temperatures in the northern hemisphere by as much as 18 degrees Fahrenheit. The warming world simply broke and locked back into a deep freeze. The period is called the Younger Dryas. It takes its name from Dryas octopetala, a small pale alpine flower with 8 petals that thrives in cold, harsh environments. Its pollen suddenly bloomed across European sediment layers as the oak trees withered away and the tundra reclaimed the land. To understand the mechanics of how the climate snapped, you have to look at the massive Laurentide ice sheet covering Canada. It had been melting for thousands of years, pouring billions of gallons of fresh water into a depression in the bedrock. This runoff formed a glacial lake covering over 160,000 square miles, a body of water geologists call Lake Agassiz. For centuries, an enormous wall of ice held all that water in place. When the ice dam finally collapsed, the lake found an outlet. Researchers mapped the floodwaters carving through the landscape, either surging down the Mackenzie River into the Arctic or tearing through the St. Lawrence River Valley. An ocean of cold, fresh water flushed straight out into the North Atlantic. The North Atlantic operates a massive heat delivery current called the Atlantic Meridional Overturning Circulation. Warm, salty water travels up from the equator, carrying tropical heat to the coastlines of Europe and North America. As it cools in the northern latitudes, this salty water gets dense and heavy, so it sinks to the ocean floor and cycles back south. It operates like a conveyor belt, driven entirely by the weight of the saltwater sinking. The flood from Lake Agassiz dumped thousands of cubic miles of fresh water into the top of that ocean. Fresh water is lighter than salt water. It floated on the surface, diluting the salt, which meant the water was no longer heavy enough to sink. The conveyor belt jammed. Without that constant delivery of warm water from the south, the northern hemisphere froze. The freeze lasted for 1,200 years. Human populations that had expanded across the newly warmed continents had to adapt immediately. In North America, a widespread population known as the Clovis culture had been hunting megafauna with distinct fluted stone spears. Right at the onset of the cold snap, those specific stone points disappear from the archaeological record. The culture fractured, splitting into smaller localized groups using different tools to hunt smaller game as the giant herds thinned out. The animals unable to migrate or handle the sudden drop in temperature died in place. There is a competing theory for what jammed the climate, and researchers still argue over it. Some scientists argue a fragmented comet burst in the atmosphere over North America, triggering continent-wide wildfires and throwing enough ash into the sky to block the sun. The proponents point to microscopic nanodiamonds and layers of soot found in sediments dating to the start of the deep freeze. Other geologists attribute the soot layers to natural wildfires, note the absence of corresponding impact craters, and point out that a melting ice dam remains a perfectly adequate way to break a hemisphere. We know the exact speed of the temperature drop because of the ice buried in central Greenland. During the 1990s, climatologists working on the Greenland Ice Sheet Project spent summers living on the glacier, drilling hollow metal tubes 2 miles deep into the crust. They pulled up long, solid cylinders of ancient frozen water, hauling the segments to the surface and storing them in specialized freezers. Snow falls every year and traps tiny bubbles of atmospheric gas before the weight of the next snowfall crushes it into ice. This process lays down visible bands that scientists can count like tree rings. The ice is cloudy with ancient air. By extracting those microscopic bubbles and measuring the specific isotopies of oxygen trapped inside them, researchers can read the exact temperature of the atmosphere for any given year. The core sample drawn from the 2-mile mark shows a thick, stable layer of warm weather, followed immediately by a sharp boundary of deep cold. Number 14. The Mediterranean Salt Giant. If you drop a drill through the blue water of the Mediterranean Sea today, past the ships and the fish, down to the seafloor, you hit mud and silt. But if you keep drilling through that soft sediment, eventually the drill bit hits a wall. It hits a solid layer of rock salt that runs beneath almost the entire sea. In some places, it sits more than a mile thick. It is called the Mediterranean Salt Giant, and it means the entire sea used to be a desert. Geologists call this period the Messinian Salinity Crisis. The Mediterranean is an unusual body of water, sitting in a hot, dry part of the world. It loses more water to evaporation every year than all the rivers flowing into it can replace. It only survives because the Atlantic Ocean constantly spills in through the Strait of Gibraltar, acting like a running faucet that keeps the basin topped up. But roughly 6 million years ago, the tectonic plates shifted. Africa was drifting north, slowly colliding with Europe. The sea floor around Gibraltar pushed upward, and the strait pinched shut. So the faucet turned off. With the Atlantic blocked, the Mediterranean started drying out. The evaporation was relentless. As the water level dropped, the sea turned into a hypersaline dead zone, killing off the marine life and leaving only microbes that could handle the brine. Eventually, the water was mostly gone, leaving behind a dry basin up to 2 miles deep. Because the basin floor sat so far below global sea level, the environment down there was entirely alien. The air pressure at the bottom would have been nearly 1.5 times what it is at the surface. Temperatures in the deepest parts of the basin likely reached 170 degrees Fahrenheit. It was a vast, blindingly white salt pan sitting squarely between southern Europe and North Africa, baking in the sun. The rivers that usually fed the sea, like the Nile and the Rhone, were still flowing, but instead of meeting an ocean coastline, they poured over the edges of the dry basin and carved massive canyons down the steep continental slopes. Beneath modern Cairo, there is a buried gorge carved into the bedrock by the ancient Nile that is thousands of feet deeper than the Grand Canyon, cut simply because the river had to fall that far to reach the empty bottom. The amount of salt left behind tells a very specific mechanical story. Normal ocean water holds a set amount of dissolved minerals. If you take a bathtub full of seawater and evaporate it, you get a thin crust of salt on the porcelain. If you seal off the entire Mediterranean and let it dry out exactly once, you get a layer of salt about 100 feet thick. But the layer buried under the sea today isn't 100 feet thick. It is up to 10,000 feet thick, which means it didn't just dry out once. The tectonic seal at Gibraltar wasn't perfectly watertight over geologic time. The sea would dry into a salt flat, and then the strait would drop slightly, or the global sea level would rise, and the Atlantic would spill back in, refilling the basin. Then the strait would close, and the whole thing would evaporate again. It was a cycle of filling and baking dry, repeated dozens of times over roughly 600,000 years. Every time the water vanished, it left another layer of salt stacked on top of the last one. The record of this was hidden completely until the early 1970s. Researchers were mapping the Mediterranean seafloor using acoustic sonar, bouncing sound waves deep into the crust. They kept getting a strange, hard echo from a uniform layer buried beneath the mud. They called it the M reflector. To figure out what was down there, a deep-sea drilling ship called the Glomar Challenger went out to pull up core samples. The ship ran its drill pipe through thousands of feet of water, chewed into the seabed, and pulled up cylinders of solid halite and gypsum. These are evaporate rocks. You only get them when salt water sits in the sun and dries up. The drill cores even contained structures built by shallow water algae, proving the rock formed in sunlit brine pools, not at the bottom of a deep ocean. The drill had found the buried desert. The cycle finally ended around 5.3 million years ago, when the land at Gibraltar gave way for good, and the Atlantic permanently flooded the basin. The water returned, the silt settled over the rock, and the sea looks normal today, but the salt is still sitting, down there in the dark, pressed under the mud. Number 15. The Carboniferous Giant Insects. A dragonfly glides through the thick, humid air of a flooded swamp, banking past the scaly trunks of towering club mosses. It hunts the same way modern dragonflies do, scanning the water below with massive compound eyes and snatching smaller creatures right out of the air. It is a perfectly ordinary predator in every aspect except its scale. This insect casts a shadow the size of a crow. Its delicate veined wings stretch nearly 2.5 feet across. This is the Earth roughly 300 million years ago. The creature is Meganura, and it ruled the canopy of a world that temporarily broke the biological rules of size. Geologists call this stretch of time the Carboniferous period. The continents were crowded with vast, dense swamp forests stretching across the equator. Trees grew aggressively, collapsed, and sank into stagnant shallow water. During this era, bacteria lacked the enzymes to efficiently digest tough wood. Millions of tons of dead plant matter simply piled up in the mud, locking its carbon in the ground before it could rot. Meanwhile, the living trees kept pumping fresh oxygen into the sky. The atmosphere of the planet fundamentally changed. The air we breathe today is about 21% oxygen. During the Carboniferous period, that number climbed up to around 35%. That chemical atmospheric spike triggered a highly specific reaction in the bodies of insects. To understand the size limits of modern bugs, you just have to look at their anatomy. They take in air through tiny holes lined up along their abdomens, called spiracles. Those holes feed into a branching network of microscopic tubes called tracheae. The oxygen simply diffuses, drifting down those tubes directly into the insect's internal tissues. It is a highly efficient system, restricted to a very small scale. You can picture the mechanism like a massive warehouse, relying entirely on open windows for air. Fresh breezes reach the outer edges of the floor with no problem, while the air in the deep center just goes stale. For a beetle or a dragonfly, a thicker body means the oxygen simply cannot drift far enough down those microscopic tubes to reach its internal organs. The breathing system acts as a hard, physical ceiling on how massive an insect can grow. The Carboniferous atmosphere lifted that ceiling. With oxygen packed so densely into the air, the sheer atmospheric pressure drove the gas much deeper into those tracheal tubes. Insects grew thicker, heavier, and wider without suffocating from the inside out. Meganura took advantage of that richer air to scale up into the premier aerial predator of its time. Its legs were armed with sharp spines to grip struggling prey mid-flight. Its mandibles were thick enough to crush the armor of other large insects. It shared these hyper-oxygenated swamps with creatures taking advantage of the exact same atmospheric loophole. Arthropleura, a millipede protected by a heavily armored back, stretched the length of a small car. It moved through the rotting undergrowth on dozens of thick legs, navigating the same flooded forest floor where scorpions grew to the size of modern dogs. The entire arthropod family scaled up to match the swollen oxygen levels, hunting and breeding in the shade of giant ferns. The reign of the giant insects ended only when the atmosphere changed again. The climate eventually cooled and dried out, and the continuous swamp forests collapsed into fragmented, shrinking islands of green. The global oxygen levels steadily dropped back down, and the heavy air thinned out. Without that hyper-oxygenated atmosphere forcing gas deep into their tissues, the massive bodies of Meganura and the giant millipedes became a fatal liability. Their open-window breathing systems could no longer ventilate their massive bulk. They suffocated in plain air. The biological size ceiling lowered back down to where it sits today, trapping insects in miniature forms. The evidence for this brief window of giants sits mostly in the coal seams that gave the Carboniferous period its name. All those thick swamp forests, full of undigested wood, eventually compressed under millions of years of pressure, turning into the massive coal beds that fueled human industry. In the year 1880, French miners, digging through one of these ancient compressed swamps in the town of Commentry, broke open a slab of dark, carbon-rich shale. Pressed flat into the dark, rock was a perfectly preserved network of fragile veins. It was a single fossilized wing from Meganura, stretching more than a foot long. Number 16. The Messel Pit Preservation. 47 million years ago, a small bat fluttered over the surface of a deep, still lake in what is now central Germany. It had just caught and eaten a moth. It swooped low toward the black water to drink, and then quietly and without warning, it fell out of the sky. It hit the surface, sank past the reach of the sunlight, and settled into the mud at the bottom. It stayed exactly there until someone dug it out of the ground, still holding the scales of the moth in its stomach. Today the site sits in a forest near Frankfurt, but during the Eocene epoch, it was a volcanic crater filled with deep water and surrounded by a dense tropical jungle. This was a hothouse world. The dinosaurs were tens of millions of years gone, and mammals were experimenting with new shapes. Early horses, roughly the size of small dogs, wandered the shoreline, picking at grape leaves. Crocodiles rested in the shallows. The area was teeming with life, but the lake itself was a trap. The problem was the shape of the crater and the water inside it. The Messel Lake was steep and incredibly deep, meaning the water didn't circulate. The top layer caught the sun and supported algae, but the bottom layers were anoxic, which is a clinical way of saying they had absolutely no oxygen. The bottom was a dead zone, and because the lake sat inside an old volcanic pipe, carbon dioxide and other toxic gases constantly seeped up from the magma deep in the crust, dissolving into the cold, still water at the bottom. Normally, that gas just stays trapped under the pressure of the deep water, but occasionally, a landslide or a seasonal temperature shift would disturb the layers. The lake would turn over, pulling that deep water to the surface, and the dissolved gas would break out all at once. It was a silent eruption. A massive, invisible cloud of carbon dioxide would roll off the surface of the lake. Because carbon dioxide is heavier than normal air, it didn't float away. It hugged the ground, forming a suffocating blanket that spilled over the banks and into the surrounding jungle. Nothing saw it coming. Birds sitting on low branches passed out and dropped into the water. Bats suffocated mid-flight. The early horses, drinking at the shore, simply collapsed where they stood and washed in. And this is where the lake's dead zone did its work. When those bodies sank into the anoxic depths, there was no oxygen to fuel the bacteria that normally cause decay. There were no deep water scavengers to tear the carcasses apart. The animals settled into the soft, fine mud, and then more mud rained down on top of them, sealing them in a geological vault. The preservation that came out of that mud is absurd. You don't just find bones in the meso pit, you find the shadows of the animals. Paleontologists have pulled up bats with the delicate webbing of their wings perfectly outlined in the rock. They have found beetles where the chitin shells still flash, with their original iridescent blue and green structural colors, 47 million years after the insects died. They have uncovered pregnant horses with the skeletons of unborn foals still resting inside them, and turtles caught and fossilized in the middle of mating. You can look through a microscope and identify the pollen grains from the last leaves an animal swallowed. But getting those fossils out of the ground was a nightmare. By the late 19th century, the Moselle Lake bed had hardened into a type of rock called oil shale. It was basically petrified mud packed with ancient algae, and it burned. Mining companies bought the pit and spent decades tearing it up to extract industrial oil. Locals would sneak into the quarry on weekends to pry fossils out of the rock, but they ran into a mechanical problem. The shale was heavily saturated with water, holding roughly 40% moisture. When a fossil was pulled out of the damp earth and exposed to the air, the rock would begin to dry. As it dried, it shrank, cracked, and flaked apart. A perfect 50-million-year-old skeleton would turn into a pile of useless dust in a matter of hours. So paleontologists had to invent a workaround, which became known as the resin transfer method. It works a bit like lifting a fingerprint with clear tape. When researchers find a fossil in the pit today, they keep the slab soaking wet. They meticulously clear the mud off the top half of the bones, and then they pour a liquid epoxy resin directly over the exposed skeleton. Once the resin hardens into a clear plastic block, they flip the whole thing over and gently wash the rest of the crumbling shale away from the underside. The rock is destroyed, but the fossil survives, suspended perfectly in the modern resin. You would think a site this valuable would be fiercely protected from the start. It wasn't. In the 1970s, as the oil mining wound down, the West German government looked at the massive hole in the ground and decided it would make an excellent garbage dump. They drew up plans to fill the most important Eocene fossil site on Earth with municipal trash. It was only stopped because a coalition of local citizens and scientists spent more than a decade fighting the landfill in court, eventually getting the pit declared a UNESCO World Heritage Site, which means the ground is safe. The excavations continue every summer, and the slabs of wet shale keep giving up their dead, right down to the scales of the moth in the stomach of the bat. Number 17. The Hangenberg Event. Roughly 359 million years ago, the oceans went quiet. At the very end of the Devonian period, the global seas emptied out their apex predators, leaving vast stretches of coastal water practically dead. The Devonian was the age of fishes. The oceans were dominated by placoderms, massive armored fish covered in thick bony plates, and built heavily enough to crush anything they caught. At the top of that food chain were the arthrodires. Dunkleosteus was the largest of them. A predator the size of a modern great white shark, it possessed self-sharpening jawbones that functioned like meat cleavers, slicing easily through the shells of giant arthropods. Placoderms ruled the open water, the reefs, and the coastal shallows for tens of millions of years. Then the ocean lost its dissolved oxygen, suffocating the reefs from the bottom up. The trigger for this collapse came from the land. Right around the time, the first deep-rooted forests were spreading across the continents. Early trees were breaking up solid bedrock with their roots, creating the first true deep soils in Earth's history. Rain washed massive amounts of those newly churned nutrients down the river systems and dumped them straight into the shallow seas. This nutrient flooding caused explosive algae blooms. The algae choked the surface of the water, pulling in all the sunlight. When those short-lived algae blooms died, the plant matter sank to the bottom. Bacteria consumed that dead matter, and those bacteria used up all the remaining dissolved oxygen in the water to do it. The process is called anoxia. It operates like a runaway rot, where the dead zone expands upward from the seafloor until the entire water column suffocates. The success of the first forests on land systematically murdered the ecosystems in the ocean. Global sea levels swung wildly while this was happening. The water dropped hundreds of feet, draining the shallow continental shelves, and then surged back up, dragging that deep, oxygen-starved water right into the coastal zones where most marine life lived. Giant armored predators required massive amounts of oxygen to fuel their muscles and maintain their bulk. When the water went dead, the entire class of placoderms collapsed into extinction. Every armored fish on the planet died out, taking the majority of marine vertebrates with them. The catastrophe bled onto the riverbanks. The late Devonian was the time when early tetrapods, the first four-legged vertebrates with lungs and limbs, were dragging themselves up out of the mud. They were just beginning to establish a foothold in the newly forming terrestrial ecosystems. The Hangenberg event nearly wiped them out too. The fossil record for early land vertebrates goes completely blank immediately following this die-off. Paleontologists call this missing time Roemer's Gap, and it is a physical void you can see in the rock layers. Before the Hangenberg event, the fossil beds show early tetrapods like Ichthyostega, creatures that looked like a heavy cross between a giant salamander and a fish, complete with 7 or 8 toes on each foot. You can track their bones right up to the boundary line. Above that line, the sandstone and siltstone layers stretch on for 15 million years, with barely a single footprint or bone fragment. The handful of survivors retreated to isolated pockets, their populations so thin they left almost no trace of their existence. When four-legged animals finally multiply enough to reappear in the rock record after that gap, their body plans have completely changed. They all have 5 toes. The modern amphibian and reptile lineages are built entirely from the genetic leftovers of whatever managed to crawl out the other side of that 15 million year silence. Geologists track this global suffocation through a specific chemical fingerprint left behind in the earth. The dead, organic matter that settled out of the suffocating oceans accumulated on the seafloor in staggering volumes. With no oxygen left in the deep water to break it down, it simply built up into thick sludge. Millions of years of heat and tectonic pressure baked that sludge into a solid band of dark, carbon-rich rock. You can find that exact black shale layer exposed in road cuts and cliffs across Europe and North America today. It sits right above the last bony plates of the arthrodires. Number 18, the Capetanian extinction. About 260 million years ago, the supercontinent Pangaea stretched from pole to pole. The oceans around it were packed with reefs built by sponges and heavy, thick-shelled marine animals called brachiopods. In the shallow waters, giant, single-celled organisms called fusulinids accumulated in swarms thick enough to build entire limestone beds. They looked like grains of wheat, and they carpeted the seafloor by the billions. On land, the top predators were dinocephalians. They were massive, thick-skulled reptiles the size of rhinos, hunting through dense tropical swamp forests. Then, the sponge reefs bleached white, the fusulinids vanished, and the rhino-sized predators died out entirely. This was the Capetanian extinction. It hit about 8 million years before the Great Dying, the famous extinction event that ended the Permian period. For decades, geologists looking at the rock record lumped the two events together. They saw the fossil numbers dropping and assumed it was a slow, bumpy lead-up to the main apocalypse. Now researchers map the Capetanian as its own distinct collapse. The trigger sits in what is now southwestern China. Deep underground, a plume of superheated magma rose from the Earth's mantle. Before the rock even broke, the immense pressure of the magma physically pushed the Earth's crust upward. It lifted a region the size of a small continent straight out of the shallow sea to form a massive dome. The marine limestone was exposed to the air, and rivers began carving deep canyons into the dead reefs. Then the crust tore open. Geologists call the resulting lava floods the Amatian traps. Basalt lava poured out of the fissures continuously for hundreds of thousands of years. It buried an area roughly the size of Texas under a sheet of rock miles deep. The magma didn't just surface quietly. As it rose, It burned through deep underground beds of limestone and coal, baking the rock and releasing its stored carbon into the air. An eruption on this scale acts like a broken planetary thermostat. First, the fissures blasted millions of tons of sulfur dioxide into the upper atmosphere. The sulfur aerosol formed a global haze that blocked incoming sunlight, plunging Pangaea into a rapid freezing volcanic winter. Tropical plants that had never experienced frost withered, stripping the forests of their canopy. Then the sulfur settled out of the air, and the carbon dioxide took over. The winter snapped directly into a brutal greenhouse hothouse. The oceans absorbed the excess carbon, turning warm and acidic. The acidic water dissolved the shells of the brachiopods faster than the animals could grow them. Warm water also holds less oxygen than cold water. The shallow marine shelves slowly choked, suffocating the remaining life and turning the reefs into dead zones. Paleontologists like Paul Wignall began pulling this event out of the shadow of the Great Dying in the 1990s. They tracked the disappearance of those wheat-shaped fusilids and mapped the exact moment the marine fossil record dropped off. The timeline of the die-off lined up perfectly with the first massive lava flows in China. The scientific debate around the Capitanian is still active. Some researchers argue the die-off was a severe regional crisis, contained mostly to the tropics, and the area directly around the eruptions. Others point to the complete eradication of the dinocephalians on land as proof of a true global mass extinction, arguing it deserves a spot alongside the asteroid strike that killed the dinosaurs. The physical evidence for the collapse is carved into the mountains of the Sichuan province today. You can hike up the steep river gorges and read the timeline straight out of the cliff faces. The lower layers are pale limestone, packed shoulder to shoulder with the shells of marine animals that lived in the shallow seas of Pangaea. The shells stack up for dozens of feet, recording millions of years of quiet, stable ocean life. Then the limestone abruptly stops. The top of the rock is scraped and eroded, marking the moment the magma plume lifted the seafloor into the air. Resting directly on top of the eroded reefs is a solid black wall of Imeshan volcanic basalt. Number 19. The Ediacaran Garden. 570 million years ago, the ocean floor was a flat expanse of sand bound together by a continuous microbial mat. Soft quilted organisms anchored themselves in that slime, swaying in the slow currents of a shallow sea. Geologists call this the Ediacaran period. The things living in that water were the first large, complex life on Earth. They were built like ribbed bath mats, flat-branching ferns, and heavy fluid-filled discs resting directly on the sediment. They survived in an ecosystem driven entirely by slow diffusion. These organisms were built completely of soft tissue. They absorbed nutrients straight from the water through their skin. You can picture it as a wet sponge pulling in spilled water. Animals grew to the size of a doormat and simply sat there, taking in the chemistry of the ocean itself. They lived and died anchored to the microbial mat, growing in repetitive fractal patterns that modern biology abandoned millions of years ago. One of the most common creatures, Dickinsonia, resembled a flat, ribbed oval. Some grew up to 4 feet long. Researchers recently extracted trace molecules of cholesterol from fossilized Dickinsonia in Russia. That cholesterol confirmed they were animals, operating on a biological blueprint that no longer exists. We know exactly how they sat in the water because of a stretch of coastal rock in Newfoundland called Mistaken Point. The cliffs there drop off into the Atlantic, and the flat rock faces are covered in thousands of fossilized impressions. They survived to be found because a nearby volcano erupted and dropped a blanket of fine ash into the ocean. The ash sank, settled over the Ediacaran seafloor, and smothered the creatures exactly where they stood. It acted like a plaster cast, sealing their soft bodies into the sediment before they could decay. One of the most famous shapes trapped in that ash is Charnia. It looks like a leaf with alternating ridges, standing upright on a little bulb-shaped anchor pad. The Mistaken Point rocks formed in deep water, far below the zone where sunlight penetrates. Charnia and the creatures around it were surviving entirely in the dark, feeding off dissolved carbon or marine snow drifting down from the surface. The very first Charnia fossil was actually found an ocean away by a schoolboy named Roger Mason in England in 1957. He pulled his specimen from a quarry dating back over 500 million years, pushing the accepted timeline for complex life deep into the Precambrian. This ecosystem held on for roughly 30 million years, 30 million years of slow growth and diffusion on the seafloor, with nothing hunting and nothing hiding. Then, roughly 540 million years ago, the fossil record shifts abruptly. The Cambrian explosion begins. Things with hard shells, compound eyes, and grasping appendages appear in the sediment. Worms learn to burrow, breaking up the microbial mats and churning the sand. The quilted creatures vanished. Paleontologists still debate the exact mechanism of their disappearance. The new animals might have eaten the defenseless Ediacaran organisms, grazing them down to nothing. Or the burrowing animals simply destroyed the microbial slime the older creatures needed to survive, burying them in loose mud. The evidence sits on those tilted sea cliffs in Newfoundland. The rock holds the shape of Charnia pressed into the stone, a ribbed imprint from a time before anything knew how to bite. Number 20. The Sturtian glaciation. Picture the planet as a smooth white cue ball drifting in the dark. Roughly 717 million years ago, ice formed at the poles and simply kept crawling toward the equator. The sheets eventually met in the middle, sealing the oceans under a solid shell. The Earth stayed completely frozen like that for 57 million years. This was the Sturtian glaciation. It was the longest deep freeze in the planet's history, sitting squarely inside a geological period called the Cryogenian. Before the freeze began, the surface looked very different. There were no plants on land, just bare stone, and almost all of that stone was clumped together near the equator in a single massive supercontinent called Rodinia. Then Rodinia started tearing itself apart. Tectonic plates shifted beneath the crust, ripping the supercontinent into smaller jagged land masses. This tearing process pushed a massive amount of fresh volcanic rock up to the surface. Since all this bare rock sat directly under the equatorial rain belt, it was battered by heavy tropical storms. Rainwater naturally mixes with carbon dioxide in the air to form a weak acid. When that acidic rain hits fresh volcanic rock, it triggers a chemical reaction. The carbon gets stripped out of the air, washed down the rivers, and locked into the seafloor as limestone. The breaking supercontinent acted as a giant planetary scrubber, pulling down the atmosphere's greenhouse gases. The global temperature dropped right along with the carbon levels. As the air cooled, the polar ice caps expanded over the oceans. Ice reflects sunlight straight back into space instead of absorbing it. More ice means more reflected sunlight, which cools the planet further, which builds more ice. The climate fell into a runaway feedback loop. It worked like a freezer door, clicking shut and locking from the outside. Once the expanding ice sheets reached roughly 30 degrees of latitude, the reflection became too strong for the sun to fight. The freeze swallowed the tropics entirely. For nearly 60 million years, the surface of the Earth was a silent white expanse. The oceans were buried under ice sheets that were thousands of feet thick. Liquid water only existed in the dark depths of the sea, huddled around scalding hydrothermal vents on the ocean floor. Any microscopic life that survived had to cling to those deep-sea vents or wait in the tiny pockets of slush where sunlight managed to pierce the thinner ice near the equator. The wind blew dry snow across continents where absolutely nothing grew. Volcanoes kept erupting the entire time. They punched through the glaciers, spilling lava that instantly froze into twisted shapes, and they steadily pumped carbon dioxide back into the sky. With the oceans sealed shut by ice, that gas could not be absorbed by the water. It just accumulated in the atmosphere. It took tens of millions of years for the carbon dioxide to build up enough to finally trap the sun's heat and force the ice to melt. The evidence for this long freeze is written into the rock record on almost every continent today. Geologists look for something called a dropstone. When a glacier moves over land, it picks up heavy boulders and drags them along. As the ice flows out over the ocean and melts, it drops those boulders into the fine, powdery mud of the seafloor. Today, you can walk up to cliff faces in places like Namibia or Death Valley and see these massive, jagged boulders sitting inside bands of perfectly smooth marine shale. Those rugged dropstones are the physical debris of the Sturtian glaciers. The mud they fell into is the ancient seafloor. You can find these exact glacial deposits sitting directly inside rock layers that formed at the equator, freezing the ancient tropics in a band of stone dated to exactly 717 million years ago. Number 21. The Chicxulub Aftermath Rainforests. South America, 66 million years ago, in the centuries immediately following the asteroid strike. The atmosphere eventually cleared of soot, and sunlight finally reached the ground again. The tropical forests that grew back under that light were entirely new. Before the impact, the tropics were dominated by conifers and ferns. The woods were widely spaced, sharing the structure of a modern pine plantation. Giant herbivorous dinosaurs moved through these trees, eating the lower branches and trampling the saplings. They functioned as a biological landscaping crew, constantly clearing the underbrush and keeping the canopy broken open so sunlight hit the dirt. The asteroid wiped out the landscaping crew, leaving the surviving flora to grow in an ungrazed world. The impact also changed the chemistry of the dirt itself. Millions of tons of ash settled over the equator, acting as a massive, sudden delivery of phosphorus. The soil became heavily fertilized. Flowering plants, known as angiosperms, thrive on phosphorus. Conifers require far less of it. This sudden nutrient spike triggered a botanical land grab. Flowering plants grow rapidly and branch out widely, and they took the chemical advantage to shoot upward. They spread broad leaves and interlocked their branches at the top, building a solid biological roof. The process was a race where one group of plants suddenly received an unlimited fuel supply on an empty track. Once they closed the canopy, they plunged the forest floor into permanent shade. The open, sunlit conifer woods were replaced by the dark, humid, multi-layered environment we now recognize as the tropical rainforest. Paleontologists map this precise sequence using rock formations in Colombia. A research team led by Carlos Charmayo from the Smithsonian Tropical Research Institute spent years in Colombian coal mines and cliff faces, pulling samples from the sediment laid down across the impact boundary. They analyzed over 50,000 microscopic fossil pollen grains and more than 6,000 fossilized leaves. The pollen acts as a microscopic census of the ancient forest. Below the impact layer, the pollen is a mixed bag of ferns, conifers, and early flowering plants. Right at the boundary line, the conifer pollen vanishes. Immediately above the line, the sediment holds a massive temporary spike in fern spores. Ferns are pioneer species, the first plants to colonize modern burn scars or landslide sites. The fossil record captures them doing exactly that across South America, right after the global fires died out. After the fern spike fades, the flowering plant pollen takes over completely. The physical leaf fossils show the structural change in the woods. The leaves pulled from the rock below the boundary are small, adapted for a brightly lit, open environment. The leaves pulled from the rock above the boundary are large, flat, and wide, engineered to catch scarce flecks of sunlight in the deep shade of a closed understory. Researchers can even see the local food chain adapting to the new jungle by looking at the insect damage on those leaves. Below the boundary, the fossilized leaves show generalized insect bites, indicating bugs that simply ate whatever vegetation was available. Above the boundary, the broadleaves show highly specific, intricate bite patterns and leaf miner trails. The insects were specializing, adapting to feed on specific host plants hidden within the dense, new canopy. The rock faces in Colombia hold the actual outlines of these broad, insect-bitten leaves. They sit pressed dark against the shale, marking the exact geological moment the modern jungle grew over the remains of the open conifer woods. Number 22. The Devonian forests rise. Before roughly 380 million years ago, the continents were mostly bare rock. There was life on land, but it was low to the ground. If you stood inland during the early Devonian period, you would see moss and small, creeping vascular plants hugging the mud near the coastlines. Nothing cast a real shadow. The wind blew across unbroken stone, vast gravel plains, and shallow streams. That changed with a plant called Archaeopteris. It was the first living thing on Earth that could accurately be called a tree. Archaeopteris had a woody trunk, branches, and soft fern-like leaves, and it grew up to 90 feet high. It spread across the Devonian world, forming the planet's very first forests. Up until this point in Earth's history, plant roots had just been shallow anchors, little threads meant to hold creeping mosses in the dirt. But these new trees needed a massive plumbing system to pull water 90 feet into the air. So they drove thick, aggressive root networks deep into the ground. These new roots physically wedged the bedrock apart. They also released organic acids to extract nutrients, which chemically dissolved the stone. This process is called weathering. On a global scale, it acts like a planetary sponge for carbon dioxide. When the rock breaks down, it reacts with carbon in the rainwater and the soil, turning it into dissolved minerals. Those minerals eventually wash into the ocean and lock the carbon away at the bottom. The first forests were essentially an uncontrolled terraforming project. They pulled so much carbon dioxide out of the atmosphere that the planet's temperature crashed. They also manufactured the first real dirt. Prior to the arrival of deep roots, water simply washed across gravel plains in wide, temporary sheets. The new tree roots locked the mud and broken rock in place, forcing the water to carve deep, winding channels. The forests literally engineered modern rivers, but pulling that much carbon out of the sky and dumping that much crushed rock into the water had a cost. All those dissolved minerals washing into the Devonian seas acted like fertilizer. They triggered massive ocean-wide algae blooms. When the algae died, it sank to the seabed and rotted, a process that sucked the free oxygen out of the water. The oceans turned into dead zones. It is, at minimum, an unusual way to cause a mass extinction. Trees just breathe the ocean to death, but geologists track a massive pulse of marine die-offs right alongside the rise of these forests. The trees thrived on land, and as a direct result, the armored fish and reef builders that had ruled the seas for millions of years simply choked in the dark. We know exactly how these root systems worked because they left casts in the stone. In Gilboa, New York, a heavy flood in the 1920s washed away a bridge and stripped the topsoil off a riverbank. The exposed bedrock underneath revealed a massive, continuous fossilized root system. Paleontologists eventually mapped out thousands of square meters of it. They found the bases of different types of ancient trees sharing the same soil, showing a complex, multi-tiered forest floor spanning the landscape. The Gilboa site preserves the exact layout of the Devonian woods from 385 million years ago. The trees themselves vanished into deep time, but their fossilized stumps are still sitting upright in the New York rock, exactly where they took root. Number 23, the Grand Canyon Great Unconformity. Deep in the lower gorge of the Grand Canyon, a flat bed of brown sandstone rests directly on top of dark, vertically tilted metamorphic rock. The sandstone was laid down roughly 500 to 20 million years ago in a shallow ancient sea. The twisted dark rock underneath it formed deep inside the Earth's crust about 1.7 billion years ago. They sit perfectly flush against each other, glued together by deep time, with absolutely nothing in between. That single contact point is called the Great Unconformity. It is a physical line where a billion years of the planet's history goes missing. An explorer and geologist named John Wesley Powell was the first person to formally document this gap. In 1869, Powell took a wooden boat expedition down the Colorado River, mapping the canyon walls as the water cut through the strata. Powell was a one-armed Civil War veteran tying himself to a chair in a rowboat to run the rapids, but his main focus was the rock passing by on either side. Geologists read rock layers like a timeline, building the Earth's history by reading younger sediment stacked on top of older bedrock. Powell realized that as he moved down the canyon, the timeline simply broke. He found horizontal Cambrian sedimentary rocks sitting directly on Precambrian basement rock. It works essentially like reading a history book, where one page covers the Roman Empire, and the very next page describes the invention of the internet, with the entire binding between them physically ripped out. Losing a billion years of planetary crust is, at minimum, a substantial clerical error. Rock does not just pause its own creation. For a billion years' worth of crust to vanish, something had to physically grind down miles of solid stone across entire continents and sweep the debris away. The primary suspect for this planetary-scale demolition is a period of deep freeze called the Sturtian glaciation, better known as snowball Earth. Around 700 million years ago, ice sheets up to a mile thick encased the globe. Glaciers are essentially slow-moving rivers of frozen rock. When continent-sized ice sheets expand and contract, they act like a planetary belt sander. Over tens of millions of years, the ice crushed entire mountain ranges into gravel, scraped the upper crust down to its roots, and carried the debris off into the deep oceanic trenches. The tectonic plates eventually subducted that crushed rock back into the mantle. By the time the planet finally thawed, the continents had been scraped flat. When the ice melted and the oceans rose, they flooded these scoured continents. The new seas deposited fresh layers of Cambrian sand directly onto the eroded stubs of the ancient, billion-year-old basement rock. The rubble of the missing era had been completely swept off the board. Geologists confirmed the exact scale of the missing time using radiometric dating. They extract microscopic zircon crystals from both layers of rock. Zircons function like tiny sealed stopwatches. When they form in magma, they trap uranium atoms inside their structure but reject lead. Over millions of years, that uranium steadily decays into lead at a known rate, meaning any lead found inside a zircon today had to come from radioactive decay. The ratio gives geologists a hard, absolute date. The numbers on either side of the canyon's unconformity are rigid. The Tepeyac sandstone on top holds the fossils of early complex marine life, while the Vishnu schist below it predates multicellular animals entirely. If you hike down to the river corridor today, you can reach out and place one finger on the sandstone and your thumb on the schist, spanning a billion blank years in a single handspan. Number 24. The Pleistocene megafauna collapse. 50,000 years ago, the planet was crowded with giants. Mammoths grazed across the northern hemisphere, tearing up frozen grass with their trunks. Giant ground sloths, weighing as much as modern cars, pulled tree branches down to eat the leaves in South America. Short-faced bears stood 11 feet tall on their hind legs, hunting wild horses across the North American plains. These animals had survived multiple ice ages, adapting to the freezing cold and the brief thaws for over 2 million years. Then, in a geological blink, they vanished from almost every continent on Earth. This is the Pleistocene megafauna collapse. It happened as the last ice age was ending, and paleontologists still argue over exactly what killed them. The debate comes down to a changing climate versus human hunting. The climate argument points directly to the melting ice. For thousands of years, a vast, dry, cold grassland called the Mammoth Steppe stretched all the way from Spain, across Asia, and into Canada. It was a highly productive ecosystem, covered in deep-rooted grasses that fed millions of massive herbivores. As the planet warmed, the glaciers retreated. The weather became wetter. That dry, firm grassland turned into muddy bogs, tundra, and dense pine forests. The giant grazers lost their pasture. Their enormous bodies required hundreds of pounds of food a day, and the new landscape couldn't provide it. The human hunting argument follows a different trail of evidence. Researchers track the timeline of when humans arrived on different landmasses, and the megafauna tend to disappear shortly after those arrival dates. Australia lost its giant kangaroos and two-ton wombats soon after humans first crossed the ocean to reach the continent. North and South America lost their saber-toothed cats, dire wolves, and giant armadillos a few thousand years after hunters walked across the Bering Land Bridge. Humans moved into new territories, bringing spears and coordinated hunting tactics to animals that had never seen a bipedal primate before. Large mammals breed extremely slowly. A mammoth might only raise one calf every 4 or 5 years, and that calf would take over a decade to reach adulthood. Even a small band of hunters taking just a few adult females a season could push a local population into a death spiral. The fossil record holds physical proof of the hunting. Archaeologists routinely uncover kill sites, digging up mammoth ribs and mastodon skulls with chipped stone spear points still wedged deep into the bone. At places like the Manus site in Washington state, a mastodon rib was found with a handmade bone projectile point driven right into the center of it. We also track the collapse through a much smaller piece of evidence. A specific type of fungus called spore or miela only grows in the manure of very large plant-eating animals. Researchers drill cylindrical sediment cores out of the bottoms of ancient lakes. By slicing those mud cores layer by layer, they count the microscopic fungus spores trapped inside. A heavy concentration of spores means a landscape crowded with giant herbivores. When you read the cores moving forward in time, the spores abruptly vanish. In lake after lake, across multiple continents, that fungus disappears from the mud layers right around the time human campfires start showing up in the local archaeological record. A few isolated pockets held on long after the mainland populations died out. As the ice sheets melted and sea levels rose, water flooded the land bridges, turning peninsulas into islands. A small population of woolly mammoths got stranded on Wrangel Island, a frozen piece of rock in the Arctic Ocean off the coast of Siberia. Cut off from human hunters and mainland predators, they survived for thousands of years. They slowly shrank in size over generations due to the limited food supply on the island. Those mammoths were still walking around the Arctic tundra roughly 4,000 years ago, leaving footprints in the snow at the exact same time the pyramids were being built in Egypt. Number 25. The Lake Agassiz Drainage. At the end of the last ice age, roughly 13,000 years ago, a massive body of fresh water sat over what is now central Canada and the northern United States. It held more water than all the modern Great Lakes put together. Geologists call it Lake Agassiz. It formed from the runoff of the Laurentide ice sheet. That was a glacier covering half the continent, in some places 2 miles thick, and it was steadily melting as the global climate warmed. The meltwater pooled in a sprawling basin across Manitoba, Ontario, and North Dakota. It kept filling, trapped inside the continental interior. A towering wall of glacial ice stood at the northern and eastern edges of the basin, blocking the water from reaching the sea. The lake functioned as a continent-sized reservoir, held back by a dam made entirely of ice. Ice makes a fairly bad permanent dam. As the climate kept warming, the Laurentide sheet retreated and weakened. The water pressure against the ice wall kept building. Eventually, a section of the dam gave way. The collapse opened a sudden spillway. Trillions of gallons of fresh water rushed out. The peak flow of the flood is estimated at hundreds of thousands of cubic meters per second. That is roughly 10 times the flow of the modern Amazon River, tearing across the Canadian bedrock. Some geological models suggest the flood surged east down the St. Lawrence River Valley, while others trace the path north through the Mackenzie River into the Arctic Ocean. The exact route is still debated by researchers, so you will see both maps. The result is the same: an ocean's worth of freezing fresh water dumped directly into the saltwater currents in a matter of months. That sudden flush of fresh water hit the ocean's circulation system. Salt water is dense and sinks, driving deep currents that pull warm water north from the equator to heat the upper latitudes. Fresh water is lighter. It floats on top of the salt. The Agassiz drainage capped the North Atlantic in a massive layer of cold, buoyant fresh water. The ocean conveyor stalled. With that warm water cut off, the northern hemisphere snapped back into near glacial conditions within a human lifetime. Temperatures plummeted, and the ice advanced again for another 1,000 years. Geologists call this sudden freeze the Younger Dryas. The climate broke because a single lake emptied too fast. We know the lake existed because the evidence is written into the dirt. The Red River Valley, stretching across the U.S.-Canadian border, is perfectly flat today. It is the bottom of the old lake bed. The sediment settled out of the still water over thousands of years, leaving behind a level floor. The region floods constantly today because the modern rivers naturally pool in the ancient depression. You can trace the borders of the empty lake by looking at the hillsides. If you drive through rural Manitoba, you can look out across the prairie and see raised ridges of gravel and sand cutting horizontally across the slopes. They sit like massive stairs stepping up the landscape. Farmers plow their fields right up to the base of them. Those are the ancient beaches. Every time the lake level dropped and stabilized, the waves carved a new beach into the rock. The fossil shorelines of a disappeared sea are still etched into the dry land. Number 26. The Deccan Traps Eruptions. Around 66 million years ago, the crust split open across what is now western India. Molten rock welled up from miles-long tears in the earth and flooded outward in continuous sheets. These fissure eruptions swallowed forests, buried riverbeds, and paved over the landscape with glowing basalt. The lava kept pouring for hundreds of thousands of years. This event formed the Deccan Traps, a volcanic province that ultimately laid down enough rock to bury the state of California under a mile of solid stone. The timing places this catastrophe directly alongside the Chicxulub asteroid impact. Paleontologists and geologists maintain a quiet, ongoing debate about how to divide the blame for the mass extinction between the two events. Some researchers argue the asteroid delivered a sudden killing blow to a healthy world. Others point to the volcanic rock to argue the planet was already dying. A third group looks at the timing of the eruptions and suggests the asteroid hit with enough force to send seismic waves through the mantle, squeezing a massive new surge of magma out of the Indian fissures. The science remains unsettled, with different teams pulling conflicting timelines from the isotopes locked inside the stone. The physical lava only buried one corner of a continent. The true harm traveled through the atmosphere. The volcanic vents pumped billions of tons of sulfur dioxide and carbon dioxide into the air. These two gases act on a climate in opposing directions. Sulfur dioxide blocks sunlight, dropping global temperatures and falling back to the surface as sulfuric acid rain. This acid altered the chemistry of the shallow seas, stripping the water of the calcium carbonate that microscopic marine organisms needed to build their shells. Carbon dioxide traps heat, eventually baking the planet. The Deccan vents injected both gases in massive alternating pulses. The global climate was forced into a violent seesaw, swinging from sudden freezing to extreme hothouse conditions. Plants withered during the cold snaps, starving the herbivores, which then starved the predators. Ecosystems across the globe grew fragile under the chemical stress. The food web was a frayed rope, unraveling strand by strand under the strain of volcanic winter and acid rain. The rock from space slammed into the Gulf of Mexico and snapped the final threads. The evidence for this dual apocalypse sits right out in the open. The timeline is locked inside tiny zircon crystals trapped in the lava, which act as microscopic geological clocks. Researchers used the uranium decaying inside these crystals to date the individual flows. They also find fossilized dinosaur eggs, bone fragments, and ancient soil horizons sandwiched directly between the layers of basalt. The animals were returning to the cooled lava plains, nesting on the hardened rock, right up until the ground split apart and the next wave of molten rock arrived. As the Indian fissures opened and closed over millennia, the lava cooled into thick, flat plains. The next eruption poured a fresh sheet of liquid rock over the cooled surface of the last one. Over thousands of centuries, these individual flows stacked up into a solid plateau. Today, Those stacked layers form the Western Ghats, a mountain range running down the edge of the Indian Peninsula. Erosion has carved the basalt into deep stair-stepped valleys. You can stand at the bottom of one of those valleys near Mumbai and look up at a mile-high wall of striped rock, with each horizontal band marking a distinct ocean of lava that washed across the continent. Number 27. The Ordovician extinction. 445 million years ago, the continents were mostly bare rock and blowing dust, but the oceans were entirely full. Early corals and sea sponges built massive reef systems in the shallow water. Crinoids that looked like large flowering plants anchored themselves to the seafloor. Trilobites scuttled across the mud in their millions. Above them, giant straight-shelled predators called orthocones, basically a squid jammed into a 10-foot traffic cone, hunted in the water column. This was the late Ordovician period. It was a world built completely underwater. And then the reefs simply emptied out. This event is the first of the planet's 5 major mass extinctions. It wiped out roughly 85% of all marine species, because almost all complex life lived in the ocean at the time. Losing the seas meant losing nearly everything. The trigger was a sudden, violent freeze. A massive supercontinent called Gondwana drifted directly over the South Pole. Glaciers began to build across the landmass. As the ice thickened into sheets miles deep, it pulled water out of the global ocean, locking it up in solid form. Think of the ice caps as a planetary sponge. The more the glaciers grew, the more the sea levels plummeted, dropping by hundreds of feet globally. The shallow inland seas, where most life thrived, drained away. The reefs were suddenly exposed to the air. The marine life that survived the receding tides was forced out into the deeper, colder ocean, where they had to adapt to freezing temperatures just to scrape by. Millions of years later, the ice melted. The oceans flooded back onto the shallow continental shelves. The survivors from the deep water were now trapped in a sudden influx of warm, stagnant, oxygen-starved water. The species that had just spent millions of years adapting to an ice age suffocated in the newly flooded seas. The mechanics of the freezing and the melting are clear in the rock. What started the freeze is a different question, and a few researchers proposed a deeply strange answer. They argue the Earth was hit by a gamma-ray burst. A massive star in a neighboring arm of the Milky Way collapsed into a black hole, firing twin beams of radiation out into space. In this hypothesis, one of those beams clipped the Earth. A 10-second flash of invisible radiation from 6,000 light-years away would have stripped away the planet's ozone layer. That would have bathed the surface in lethal ultraviolet light and triggered a chemical reaction in the atmosphere, wrapping the globe in a thick brown smog. The smog blocked the sun, the temperature crashed, and the glaciers took over. Take that specific theory with a grain of salt. It remains highly debated, and most geologists point to simple shifting tectonic plates and a disrupted carbon cycle to explain the sudden cold. The extinction itself is permanently logged in the fossil record. Geologists find a sharp, clean line where the diverse trilobite species and the early corals just stop. Right alongside that biological dead zone, the rocks tell the story of the missing water. Moving glaciers drag rock and debris across the ground beneath them, carving deep, parallel gouges into the earth as they slide. Geologists mapping the rock layers from the end of the Ordovician found those massive glacial scrape marks. They found them cut directly into the bedrock beneath the sand of the modern Sahara Desert. Number 28. The Chicxulub, day after fossils at Tanis. Deep in the Hell Creek Formation of North Dakota, an arid stretch of badlands holds a deeply buried riverbank from the late Cretaceous. Inside a meter-thick layer of rock, researchers found a chaotic mass of sturgeon, paddlefish, marine reptiles, and charred tree trunks. They were all tossed together and locked in mud, pointing in the exact same direction. This is the Tanis fossil site. The team excavating it argues it records the exact afternoon the Chicxulub asteroid ended the era of the dinosaurs. North Dakota sits roughly 2,000 miles north of the impact crater in the Gulf of Mexico. A standard ocean tsunami would have broken against the ancient coastline long before reaching this deep inland. The force that buried the river valley was a seismic wave traveling through the Earth itself. When the asteroid struck the Yucatan Peninsula, it triggered an earthquake millions of times more powerful than anything recorded in modern history. Those seismic waves rolled through the continental crust at thousands of miles an hour. When they reached the inland river systems of the Dakotas, the ground violently shifted. The water in the river channel acted like a bathtub being tipped upward. A 30-foot standing wave, called a seiche, rushed backward from the sea and up the river. It tore apart the banks, scooped up everything living in the water, and slammed it onto a massive sandbar. As the fish lay thrashing in the receding mud, the sky started raining glass. The initial impact had blown millions of tons of vaporized seabed straight up through the atmosphere and into space. Up in the cold vacuum, that material condensed into tiny molten glass beads called spherules. Gravity pulled them back down. They re-entered the atmosphere, falling like glowing hail across the continent. At Tanis, this glass rain pelted the mud and splashed into the remaining pools of water. The fish were still breathing. Paleontologist Robert De Palma, who led the excavation, found dozens of these tiny glass beads wedged deep inside the fossilized gills of the sturgeon and paddlefish. The animals had filtered the impact debris straight out of the water in their final moments, a claim that cleanly ties a single fossil bed to a specific hour of prehistoric time draws heavy fire. The scientific community is still actively debating the site. Geologists point out that river systems are messy. Currents constantly dig up old sediment and mix it with new material, creating the illusion of a single massive event when looking at a compressed rock layer millions of years later. Some peers argue the Tanis site is the result of a standard river flood that reworked older impact glass into a newer bone bed. The evidence trail supporting the day of theory relies heavily on the chemistry of the glass itself. The spherules recovered from Tanis perfectly match the radiometric age of the Chicxulub impact, 66 million years ago. Inside a few of those untouched glass beads, researchers found unmelted fragments of rock. The chemical signature of that rock is a precise match for the crust beneath the Yucatan Peninsula. The sediment at Tanis shows a massive, sudden surge of water, immediately capped by the fallout of an asteroid. And locked in the center of that rock are the fish, preserved with the glass from the crater lodged in their gills. Number 29, the Doggerland drowning. 10,000 years ago, a hunter standing on the eastern edge of what is now Britain looked out over a sprawling, gently rolling plain. Dense marshland, river valleys, and heavy brush stretched unbroken all the way to modern-day Denmark. Herds of reindeer, wild horses, and mammoths moved across the grass. Bands of human hunters followed their tracks, setting up seasonal camps along the riverbanks. This was Doggerland. It held some of the richest hunting grounds on the European continent. During the height of the last ice age, so much of the Earth's water was locked up in massive continental ice sheets that global sea levels were hundreds of feet lower than they are today. Britain was simply the northwestern peninsula of Europe, anchored to the mainland by a stretch of habitable land roughly the size of the modern United Kingdom. The people living there had no reason to know they were walking on a temporary landscape, but as the global climate warmed, the ice sheets began to melt. That locked water poured back into the oceans, and sea levels started to climb. The drowning of Doggerland was a quiet, generational erasure. The water crept inland by just a few feet a year. A coastal marsh where one generation hunted waterfowl would become a saltwater bay by the time their grandchildren were born. Over a few thousand years, the creeping ocean turned the river valleys into estuaries, then turned the high ground into peninsulas, and finally cut those peninsulas into shrinking islands. The people living there packed up and retreated to higher ground, walking westward into Britain or eastward into Europe, as the water closed in behind them. By about 8,200 years ago, Doggerland had been swallowed down to a low-lying marshy island roughly the size of Wales. Then the Norwegian continental shelf collapsed. That underwater landslide, known as the Storegga Slide, displaced an enormous volume of seawater and sent a massive tsunami rolling south across the North Sea. The wave washed entirely over the remaining islands of Doggerland, tearing up the coastal camps and pulling the last of the land bridge into the dark. For decades, geologists mapped this landscape entirely through ocean depth charts. Then the commercial fishing industry provided the physical evidence. A trawler dragging the bottom of the North Sea is designed to catch cod and haddock. It is generally an inconvenience when the nets come up heavy with 100-pound mammoth femurs. Starting in the early 20th century, fishing crews routinely hauled up the remains of woolly rhinoceroses, lions, and reindeer from the deep water. Later, oil and gas companies began running seismic surveys across the seabed, bouncing sound waves off the ocean floor to search for drilling sites. Those seismic maps allowed researchers to precisely trace the deeply buried riverbeds and the exact outlines of prehistoric lakes, sitting beneath 100 feet of cold salt water. The trawlers also brought up proof of the people who lived there. The final record of the hunters who walked across that lost plain came straight out of the commercial fishing nets, which dragged up carved bone harpoons and perfectly shaped flint hand axes from the bottom of the sea. Number 30. The Shark Bay stromatolites. In the hypersaline shallows of Shark Bay on the western edge of Australia, lumpy gray mounds sit half submerged in the tide. They resemble smooth, weathered boulders, resting entirely still in the warm water. These are living structures called stromatolites, built by microscopic organisms working in the exact same way they did billions of years ago. Stromatolites are layered mats formed by massive colonies of single-celled cyanobacteria. The water in Shark Bay is twice as salty as the open ocean, which keeps snails and other grazing predators away, leaving the bacterial colonies completely undisturbed to soak up the sun. And they use that sunlight to build. The mechanics are entirely physical. The cyanobacteria secrete a sticky mucus film over their colony. When the tide rolls in, floating grains of sand and dissolved minerals get caught in the slime. As that trapped layer of sediment hardens and begins to block out the sun, the microbes simply push their way upward through the grit to reach the light again. They secrete a new layer of mucus, trap more sand, and repeat the cycle. The colony operates like a biological 3D printer, running in extreme slow motion, laying down millimeter-thick sheets of limestone over thousands of years. These specific bacterial colonies are the surviving architects of the Great Oxidation Event. Roughly 2.4 billion years ago, the ancestors of these exact microbes covered the shallow continental shelves of the early Earth. They spent eons photosynthesizing, pulling in sunlight, and pumping out free oxygen as a biological waste product. That waste gas eventually saturated the oceans, rusted the dissolved iron out of the water, and filled the atmosphere. They flooded the planet with oxygen, creating the baseline chemistry required for complex life to evolve. Geologists track this timeline by looking at the fossil record a few hundred miles away in the Pilbara region of Western Australia. The ancient rock formations there contain fossilized stromatolites dated to roughly 3.48 billion years ago. When researchers slice those ancient stone mounds open, the cross-sections reveal the exact same stacked, wavy bands of sediment. The living gray mounds in the modern Australian shallows are actively depositing the same millimeter-thick layers found trapped in the oldest preserved rocks on the planet.